Hello, good morning, everyone. Today is the second day of the South American Conference on Visible Light Communications. I expect that today enjoy of the seminar and the conference. Yesterday, we had a very interesting presentation about the state of the art of the light visible communication. We have some information about the recent papers presented. And today we will continue with the same discussion and interesting sharing information. The first activity today, I will invite our first guest speaker, Mr. Osman Younis for Northumbria University. Please come here.
Good morning, everyone. Just to familiarize myself. Good morning, everyone. First of all, I would like to thank the organizer, everyone, whoever arranged, invited us, organized the event. It was the first time for me in this such a lovely country. I think for the first time for me from a Latin American country as well. So I came from the Far East way. So my name is Osman Younis. I'm originally from Iraq, is a Middle Eastern country, so it's very far from this area. Yeah. So a brief introduction about myself. I studied in Northumbria University. I migrated to and started my master, doing my master with Professor Fari, who is presented here. And I did my PhD as a part of the optical communication research group led by Professor Fari again, you can see it. In Northumbria University, and I'm currently a member of different laboratory. Basically active member in ECRN is the one that's been presented by Professor Stan yesterday, as well as led by Stan and Fari as well. And yeah, today is our I will basically go through a brief introduction, or let's say a bit of thorough about the optical camera communication. So I will have a gradual complexity level. So sorry for those who are expert in the field. So we'll start with the beginning introduction about the topic and going forward in that. So I hope you will enjoy it, and I will go again with the thing. So here is the content of my topic today. So it's just to introduce to basically, hopefully that most of you are familiar with the concept of VLC and the moving on in the concept of that optical camera that was. Even yesterday, we have a brief presentation from Vicente about that, and moving into some related project and overview of what we do, and then as a final comment on that. So I just start with maybe a simple slide and saying, why do I need a new wireless? As you know, when we do anything, any concept, anything, it's driven by a need of something, yes? Otherwise, there will be no need. So here is a simple of, maybe I want to engage with the audience and to get more people involved in that. And it says, why do I need a new wireless? I mean, what will it bring for me in principle? What will I get? You can see here is some people saying, it depends on the research you do. It's just the direction. I just put that forward to show, what is the benefit of doing that wireless, and why do we need that amount of scientists doing this research, and what is the significance of that research? So I'm just to get everyone engaged. Please, if you do have a smartphone, just scan that one or put this, and you can put a reason for that, and you will straight away, it will appear in the slides. So let's have an opinion of what do you think about the benefit of that? It's a bit of engaging. It will not take more than 3 minutes, 4 minutes. So just comment. Yes, maybe start with that.
Because we want more trouble.
Yes, okay, yeah. Maybe we can start with you, Ijaz, yes?
Yeah, I mentioned we want more trouble. So we want more challenges.
More trouble, all right. That's a bit of this. Anyone have any say on that? Okay, we do a research on that. I mean, we have to be driven by something, yes. So why I'm doing that research, why I'm actually looking for a new wireless, what is the benefit of, I mean, yesterday I've seen some presentation saying that the driven is like, let's say ultra low latency, for example, to get a low latency signal for a use of, I don't know, this, okay, I guess no one is putting any comments. So once you scan that one, you can, whatever you comment, it will appear in here. So,
Really?
yes.
I really didn't. I was writing because we want more devices.
Okay, okay, strange.
Better qualities of service.
Okay, better quality of service. Anyone else, maybe? Cyber security. Okay. Any other comments on why do we need actually wireless or a new wireless or a new technology? 6G, 5G, 3G. Coverage to cover more areas about internet. Okay.
Application demand.
Application on demand, basically part of Internet of Things and so on. Okay, these all are actually right one. I'm not sure why we are not able to see that, but probably I will go forward on that and we can continue with this. So I just adapted some slides from concept that about Fari was developing and with the help of actually AI, and it's like, okay, let's go through the revolution and what we have done as a human from an industrial revolution point of view and moving forward to the invention of that concept of wireless. You can see here is moving from the first generation where people actually start to use machines in order and power machine in order to basically achieve their need from a lot of basically industrial revolutions. You can see this is in the 70s and moving forward in that, you can see that this is led to the mass production of electricity, the invention. When the electricity came, it changes the life of the human. And then the third revolution then coming from the IT and basically the concept of automation where we start to use machines to do things for us. And then the last, basically what they called it and trying to categorize them is the fourth generation where, as you say, the mention of the cyber and physical security and system and automation things, that is the 25th centuries they're presenting. This can include all of whatever we have talked about from providing, then they say that different types of communication technology, cloud service. You talk about robotic, drones, virtual reality, wearable devices, smart environment. All of these can be a part of this current trend of whatever we have progress as a human, let's say, from a general point of view. So again, here we talk about what communication technology that have been currently. I mean, if you get an overview of what is the communication technology that we currently have, and let's say people are seeking in research, mainly, I just put forward one of the things is the CubeSat-based laser communication. I mean, the need for the space, you can, if you go now, a lot of research, a lot of areas that working on CubeSat. For example, a CubeSat is a concept of having a small satellite that to provide a coverage for basically a large area from the space, and that basically miniaturized satellites, a small size of satellite, and that actually to provide the low, basically a power efficient, low mass, and provide the speed with this. So one of the, now you would see a lot of communication based on that concept of having a CubeSat communication. Another concept that is emerging research now, you can see the quantum communication, but where we use the quantum mechanics instead of the classical physics rule in order to basically provide the communication. I mean, what does this offer to us? You know, mainly a lot of research works from a concept of security, which is like quantum key distribution. So where actually it has a basis of superposition, entanglement, potentially offer a high speed because it's a parallel processing is compared with the normal classic physics. So a lot of research also looking into the quantum communication and that concept of having this, and a lot of research, a lot of progress on that concept of communication. Again, the need for the communication for having an extended reality and virtual environment where you need actually access to a lot and high bandwidth, where people demand the need for that one. You can see that a lot nowadays in augmented reality, mixed reality, immersive reality, metaverse, all this under the single umbrella of that extended reality, basically, where you have to augment virtual photos or virtual things with the real environment to provide a blended environment for the users in which they can benefit out of that. Moving forward, the Internet of Things, nano things, you can see that a lot of actually now also, I would say, research going that direction, where you look into the nano things, for you have a, for example, nano sensor that can nodes, can be, for example, monitoring environment. It can be like for drug delivery, where you want to target cells in the human, for example, in a nanoscale. So you can have, we seek that way of communication and look for that point of internet nano things, where you want to provide that communication to these nodes and cells in a different level. So this basically type of communication technology that actually we look into it and say, okay, this can be a beneficial, and that we can seek a need for this in order to provide coverage, for example, need for nano for illicit drug, for a lot of examples, basically advancing the need of that communication technologies for a human. Okay, again, I will just go briefly about some of other technologies that is actually adding to something to this communication. And you have, if you look into research, you can say, okay, starting from intelligent reflective service, again, a new way of communication, of helping basically the data to be steered to a users, to have basically, again, controllable element where actually you depends on the phase and the user, and you can target the propagation of the light signal or the wireless signal towards a user, whether it's a RF domain or a light domain. Again, a blockchain technology is a different way of having spectrum sharing, for example, to provide service and quality of service to user along the way. You can see that with a lot of concept of 5G. Beamforming is almost the same as intelligent, with a different way of looking at it. Actually, is directing the narrow beam with a high gain to certain areas in order to provide that high quality of service, or let's say service on demand for users. You can see that from an RF point of view, as well as from a light point of view. Cell-free communication. Okay, you have, so we progress as okay, we used to have a base station where the data is sent to the central station. The central station will redirect that signal to a user. Cell-free is actually, regardless of having a base station as a principal one or a central one, you basically decentralize it, and you have a, regardless of this, you can communicate with each other. You can find a lot of now technologies like, for example, NFC or whatever. This can be a decentralized one, because you don't need to access a main server for that, or a main station for that. So this is actually a brief way of looking into this. I mean, this is just a general view on this. Okay, I'm trying to, okay, sorry. Okay, looking into going ahead of this, you have the research about that millimeter wave, and that you have the basically going into high frequency, several hundreds of meters. You can, this concept of being introduced with the part of 5G on beyond, let's say, for a lot of basically communication technology. You can see here's even a terahertz bandwidth is a tens of meters. You can see the way of you designing the antenna and having basically multiple sources to send the information with a high frequency. Again, this can be questionable to some level from a radiation point of view, of hazard point of view. Okay, so moving forward on that, I mean, that's, as we also going into the same principle of that conference, basically this leads us to the need for optical wireless communication, and the concept that been actually most of attendees hopefully are familiar, and for those who are not familiar, we'll get to know more about it. And the concept of having visible light and infrared and ultraviolet, basically having access to the optical wireless visible and invisible band that been now looked at, and from the point of view of having this gathering as well as to hopefully strengthen that field. Okay, the concept here is going from we have a lot of basically the visible light wavelength spectrum. You can see here, we tried to actually exploit that spectrum and availability for that one for communication purpose, or having a hybrid system where actually you combine all together to provide an optical wireless communication system. Okay. Okay, sorry. So moving forward for the light, okay, I'll try to summarize, okay, what kind of light sources, what kind of optical domain, and what we have done as a human so far from having a light source, and how do we actually use these as a source for information, delivering information as well as for lighting. So you can see here is a simple AI generated content of the light sources actually going from 80s and going forward in that, and we will actually look into them one by one in here. So starting from having a light as a source of heat, communication, being used significantly in the past, I would say, moving into I was looking in literature and having that in the 13 BC, where people were actually worshipping that sun and the light source, basically moving that. And you can see that as in the Egyptian culture, I guess Akhenaton is that one of in the museum. You can see here is the light, where people actually worshipping the sun. Okay, moving forward in that one. So moving forward, having the candle, and again is 1800. You can see the light in candles and being used for communicating the information, where you can have a candle to lighting basically the way of communicating. Moving forward in the 18, where you can see here is the progress into advancing of actually manufacturing and progressing of having these light sources. You can see the first incandescent lights is T79. Moving forward in 1960, where the laser was introduced. Again, the progress led to having an LED with a different way of having LED light sources, where you can actually use this, which is the principle of having that optical wireless. We can for the visible light domain, where you can switch this with a certain speed in order to deliver the data. You can see here's again, this is with a short period of time. You can see the progress in light sources is actually phenomenal, and you see that the invention, like for example, the incandescent, it was adopted in 1870. It was started to vanish and rely on the LED as a alternative way of basically lighting the environment, where you provide a much more different way of actually looking in the lighting point of view. Here is I just provided some cities where they completely, and towns, adopted the LED as a light sources and abandoning the incandescent light weight. So you can see, okay, the first LED used in a vehicle, basically headlamp. The first city was lit entirely in Italy, one of the cities. Is it? You can see they moved to use the LED. So that's why actually one of the drivens for us to actually look into the visible light as a way of communication. Again, what does it offer us instead of RF? Probably most of us hopefully know about that. And for those who are beginner, again, it's just the multipath. Basically, the multipath is much reduces compared with RF because it's more directional. You don't need a bandwidth regulatory. So I think it's already been mentioned before some presenters. You can consider that to some level an energy efficient way, because you're blending the light as well as the communication for the same source. Again, from a concept of security, because it's a highly line of sight and you need directivity, therefore it can be considered an enhanced security offering. You can have a lot of concept of the spectrum availability, no electromagnetic, it offers to somehow, so you can see a lot of actually advantages for having the use of optical wireless instead of the RF, or basically as a complementary technology to add that on top. I mean, these are one of the main guidance and driven unit of why are we actually looking into this research. Yes. We will actually question this at some point, and we'll come back and say, okay, we'll do that and improve that and look into each individual unit. But here you go, from a spectrum point of view, you can have access to 400 terahertz, like to 800, 400 to 800, if you use that available of that spectrum as compared with an RF. So now this, with the progress of Internet of Things, all of this technology, I mean, we look for alternative way of looking into communication to provide a way and facilitate our actually way of looking into things. Okay, here you go. Is a way of actually one of these advances of the LED and manufacturing. You can see that blue LED where light is actually, if you look to the wavelength and you have a certain beam width, and that actually the pulse of that light is coming out of this, and this is, you can offer basically a different wavelength of communication. This is a simple way of looking into visible light, for example, moving into having the concept of RGB, the different way of actually having a light sources with a 3 color, and this is again the bandwidth and the spectrum basically that allows us to utilize that spectrum for that. So again, this is the way of looking into the spectrum and looking for the communication point of view. I'll just again move forward with this. I think these are sort of more introductory into this. Again, for the LED, the user, you can see it offers a high luminosity. You can see this is basically lifetime. It offered much longer lifetime in terms of compared with the different type of these light sources. I mean, you can see the concept of having LED to provide basically low energy consumption, reduce carbon emissions, and basically to be utilized as in more often in our day-to-day lighting systems. So here is again just from a marketing point of view. So you can see the market expectation is growing rapidly for the use of this LED. So now if we look into this LED more deeply into, okay, what can we gain out of this? I mean, looking into sending this data, how fast can we switch these LEDs in order to transmit our data? I mean, is that possible? How fast is that can go? Then this give us a little bit of more knowledge about this, of having this. And basically these light sources were the bottleneck of having a communication high bandwidth for the optical wireless communication in general. Yes. Again, I'll just list this very fast. Again, here you go. Different light sources having an OLED, for example, 1 meg, less than 1 meg. Okay, moving into a blue LED concept of being invented recently. It's a Japanese scientist and he got Nobel Prize for the invention, 2014. Again, that offers a few megahertz bandwidth for the transmission. Different light source RGB concept offer like a bandwidth of up to 20 meg. You have a micro LED where it can a smaller size but higher bandwidth. The way of looking into actually providing and the semiconductor design itself, you can have a higher bandwidth, relatively higher bandwidth as compared with the other previous one. And again, the white LED and the blue phosphorus one, and you can offer over 100 meg. These are reported already and been invented and it's already exist in the market. Okay, this is from a transmitter point of view. Now, to more indulge in that and getting more in depth. So we have this information being transmitted. Now we're looking for the receiver point of view. Okay, so as a basics receiver that been used in literature and the semiconductor design, we have maybe, I could say 3 main types that we've been used to receive that signal. From a pin diode point of view, avalanche photodiode that offers a higher bandwidth but a higher sensitivity. And the concept of having multiple pin diode that is in a set in array, and that to receive in actually presented by an image sensor that can be commonly referred as camera basically. And that another way of you having these arrays of photo pin diode that is being structured together to capture the light within a certain speed, and therefore allowing the receiver to capture the signal. So these are the main ones. So now we are going more into these receivers and looking into more in depth in the camera, because this is one main topic for today. Okay, so basically why I'm using camera now is moving from the concept. We moved actually from concept of different communication towards the optical wireless. Then we move into the light sources and moving into the receiver. And now we are looking into the optical camera as a receiver for us. So use of camera, a lot of people been used. I mean, yesterday we heard 2 presentations from Vicente again about having camera and camera communication and the need for the camera communication. Now we will go a little bit in depth into that. So what does it offer us? A massive MIMO light source. I mean, to give an idea of this, I mean, that was suggested. We were walking with Pari yesterday, and we were passing by a mall in here, yeah? Probably the people in here more aware of this mall, yeah? Fragarago. I'm sorry for my Spanish accent because I don't know how to pronounce it. Yeah, you can see here the concept of multiple light source set together. Each of them can be treated an individual light source that you can actually modulate, send the data and receive that and offer that special modulation, different special wavelength. You can see different color, and these can be actually utilized for a certain communication schemes. You can actually use these for some certain cause or some certain application. This is one of the main triggers for using cameras. Okay, that can offer massive MIMO. This cannot be offered by a simple single photodiode. Again, moving forward from that concept to a concept of mobility, cameras actually now having a handheld mobile phone that can have a camera that actually provide you with a mobility feature. I'm sure everyone almost have a single or more than one single camera that have actually offered that feasibility for the use. And again, from a concept of availability, you can see now how many mobile phones being utilized in the planet. Okay, so this we actually make a good reason for the utilization of these cameras as a receiver and say, okay, here is my reason, look into how many cameras are existing in the planet, and then we can use all of this as a receiver from a light source. Again, looking into market point of view, you can see this is a growing industry, and you can see expecting like a huge amount of money that been pumped into the utilization and manufacturing of these cameras, and specifically here in the CMOS camera, because it's mostly utilized for the smartphone, handheld, and devices. So here is just a summary of annual growth of 10.5%. Okay, here is an example of, if you look into the standardization for this utilization of the camera and what application it was already been, some of them has reported actually in literature. You can see from advertising point of view, you can have a camera, look into a panel light source that can capture a data out of this. You can have an application for, again, is like you can see in a MIMO for providing augmented realities application where actually camera look into things and showing you differently based on whatever that the information want to be communicated. For again, different security purpose from hazards point of view, you can utilize these for use of actually vehicle to vehicle and automobiles, actually vehicle communication, another way of looking into providing smart cities, smart system where actually you look more into camera driving you towards your destination without the need of any interference from that point of view. Again, from an application point of view, yeah, you can have from extended reality, you can see this is an application that exists. Again, IKEA, if you're using them, they have an app for that. This is being introduced. Again, tracking localization, another way of looking into things. Okay, I am lost in the city. Where I go, I just hold my phone and it tells me where I am based on a simple capturing this. Another way of communication, enhancing security. Again, for that, you can see my biomedical application where camera can be attached and something looking into depth and basically providing more about vital sensor activity about the human and communicate that to other. You have some research that been done. Again, indoor communication where you actually lack access to GPS and so you or clone as basically satellite where you actually need an alternative way to position yourself within building an intelligent transportation system where we actually highlighted previously. Okay, more about application. You can see now application, you can have an underwater communication. And again, some of this content in AI, and I already mentioned this is content is being created to keep this okay. For non-line of sight communication, one of the way of presentation yesterday, again, Vicente was probably looking into some way of this. You can have a light source camera looking at a different place and getting the data out of that. These all are a different way of communication that actually camera can be utilized for and have found its application with. Okay, getting more in details of this, I mean, I use one of the slides that Fari was presenting previously here for the looking in depth of the camera actually is, okay, if I'm getting an image sensor and I'm looking, okay, let's break it down. What do we have in here? And how do we actually, where do we have to look at in order to activate or enable that camera for a communication point of view? So as a common sense, you can have, usually this is camera looking into a lens system as a beginning. You can have a lens in order to focus the light, basically getting more of the magnifying the signal. You get an aperture with a different opening in order to control the amount of the light that is passing into the sensor. This is a common basically aperture available in the market. Moving into the concept of shutter, where actually how does this signal are captured? We have this concept of rolling shutter, global shutter. This is actually the gradual way of capturing the light, depends on a certain exposure time, which is the time that in which that light sensor is exposed to the light. Moving into another ISO is magnification. Okay, it's just it can be a software magnification where how much you want to amplify the signal being captured in order to be able to receive that signal. Moving into quantization, again, this is the way basically the shutter speed and the ISO and the aperture based on the opening of that camera and that gain and the speed of actually capturing that light signal. These are three main parameters that we can actually explore in order to look of how do we enable the use of that camera to receive the data. Again, once the data is captured, you look into the quantization, analog to digital converter, and the way that actually you convert that signal in order to be received in or decoded in the way that we want that is a quantization. Different filtering, that this is one of the filters before the coloring way. You have a RG and a blue one. So debayering filter, you can see is a way of, okay, how do we capture the color from a different perspective? So the sensor will provide that filter, and usually they have all this, and this is the steps and procedure in order to get the different wavelength than this. And we have, again, a gamma correction is another way of actually looking into how I actually correct that signal that being captured and control that lighting in order to ensure the optimal reception of that signal. This can be from a vision point of view as well as from a receiving communication point of view. Okay, moving forward to the communication point of view of that, how do we establish that use of that camera for receiving the data? Okay, we already established having a light source that can be LED, LCD, micro LED, different light of source. You encode the signal and you choose your modulation schemes. You send that, you have an optical channel. You can see we look into a different either spectrum or intensity, and then you transmit that signal over a light source. Here is a rolling shutter as a very, very nice multimedia was actually adopted from here, my previous colleague in Spain, Cristo. He did design very nice way of actually a video of demonstrate, okay, how you can see that flickering of that light with some certain speed. This can be captured, and then based on that capturing of that light, you present the signal and you're decoding it and processing it afterwards. So this is actually how I basically establish that optical communication link in a very simple way and looking into it. So moving forward of that. So here what I'll introduce the project that some of them I did as part of my PhD, some of them moving forward in that and getting in depth of this project from this. Okay, again, AI generated content. I was asking the machine, can you provide me something that can make it more realistic for people to understand? You got a light source, pick up your phone, you can get a signal, whatever you want, you can treat it with a different way of looking into things. okay, we looked into establishing that data communication. Now, what problem? I mean, if I want to do that, why I'm not seeing it more often? What is the common problem of having these cameras or utilizing these cameras? So basically, we mainly look into the 3 different problems of having these cameras. Okay, firstly, flickering. If I have light switched in a low frequency, I could be actually causing a lot of problem in a human and health hazards for individual who looked at it. So you can see that light, it flickers. You cannot imagine that having this in a normal, at least some scenarios of indoor, maybe outdoor, maybe it could be in some certain cases you can actually work and having it. But in general way, for a normal lighting system, we cannot afford having a light flickered for a human eye. And this is, I got it from a normal source and looked at it, is this. So flickering is one of the huge, or let's say key factors that is enabling the communication in using optical camera communication. Again, the camera, this has a, you can look into solving that from having high-speed camera where actually you have a slow motion, you can have a lot of data rate, for high frame rate data, you can actually use high switching facility as well as high-speed camera, but this can be, again, daunting and it was not feasible to everyone. Having that concept of a global shutter, rolling shutter, again, looking into encoding scheme, looking into modulation scheme, this could be one of the solutions that you can actually look into that power of that having a switching and getting rid of it. But we will get more into this at the coming slides. Similarly, from the bandwidth limitation, okay, that exposure of the camera, it will be exposed for a certain time. You can treat it as a low pass filter where actually has a limited bandwidth, because the fact that once you stop that, you actually trade off between the bandwidth and the light that is actually pumped into your camera. So basically, once I expose the light to a certain time, once okay, this is my timing, I'm allowing this power to come in, however, at the cost of having a low pass filter where maybe you get this rigged pulse, it can be a limited bandwidth. This is one of the actually, I measured the bandwidth of the normal camera and you can see it's very low. We talk about in a few hundred hertz. Again, another problem of having a blooming effect where actually the light is intense, the camera cannot capture it. Another problem, people might suffer from this, even from a vision point of view. If you pick up your camera, light it into a light source and try to get it, you will have what is so-called blooming effect, where actually then the pixels inside this array will be saturated and you no longer be able to capture the signal correctly. Okay, so now we will have, starting from looking into bandwidth problem and looking into, okay, how do I push that from a point of view from communication? A different way of actually looking into this, we look into color, wavelength, intensity, and the shape of that signal that being transmitted. Here is a way of actually different way that you present and encode your data. So based on that one, you could push a little bit the bandwidth to some level and making it feasible for some certain application. Equalization is another way of actually looking into the problem. Equalization is a pre or post equalization is one of the commonly used technique in wireless communication for mitigating that inter-symbol interference in another problem and pushing the signal forward. Here is some of the literature that actually talk about equalization concept, from having a double equalization, pre and post equalization, to the use of artificial neural network, the current advances in order to enhance the signal, which I work actually throughout my PhD on that, and we will see that in the coming slides. And again, you can have an ANN-based artificial neural network-based decoder. We design a decoder that you can actually enhance the signal and getting back based on the decoding scheme that's been supported by the AI. Okay, here is more in depth of looking into the modeling of that image sensor and having it to sort out and solve the issue of that bandwidth that we have just talked about. Imagine you have a rolling shutter concept is mainly for the rolling shutter, and this each line of that rule exposed to a certain time, it could be in millisecond, and this will lead to, again, to having that rigged pulse, and that will have a basically certain bandwidth limitation. And you can see here is following with the sampling process that to have the quantization that we actually mentioned previously and getting the signal. Here is from a mathematical point of view, okay, how I can get that voltage out of this signal that being transmitted to me. Again, looking into frequency domain of that is just a way of tackling the issue. And then you can see it's looking into a problem of, again, having that exposure time will have to sacrifice either a bandwidth or basically the DC gain, the light that comes into the signal. So whenever I get lower band, if I want to push the bandwidth, I have to sacrifice with the gain, meaning that I have to sacrifice with the light that is pumped into that light source and image sensor. I hope that concept is so far is being delivered and everyone is actually getting the idea of this so that we can proceed forward. This is one of my works in that field, okay, using systems. We have an encoding scheme, Manchester encoding schemes to ensure that signal being basically transmitted equally. Each bit you have equal distribution and you get a certain protocol that been designed in order to establish the communication, the data being sent. You can see this is a captured by image and then is downsampled and recovered. So that signal here, we got that signal. You can see the signal in here that been recovered with a certain this. So you can see that, okay, this is the more specific about the header, okay, the payload that we designed here. You've got, okay, we measured we look at from a signal to noise ratio from a different perspective in here in the image point of view, in which we actually sum all the rows that represent 1 bit status and the intensity of each row is accumulated intensity of each row. This will represent the power of that bit or the energy of that bit and divided that by the signal after getting the DC gain. So we will get, and here we getting this data, okay, to design a equalization using AN. You get the signal, you transmit the signal, you get the signal, and then we do the synchronization and go having a machine and telling the machine, okay, once you get this means that the status is 1 or 0 with some certain training samples, and using this sample actually to train these data. And this is actually more in depth. Okay, you can based on these data, you can train your system and having basically ideal system where you get rid of this rising time and falling time using a simple neural network, a single hidden layer, no deep neural network. It's just a simple one. And you train that and you look into lookup table, getting these equalization, just like nonlinear equalization, where you look into this coefficient and you get that and feed that to a system and use that eventually for recovering the signal and decoding it efficiently. Okay, this is we looked into different basically algorithm in order to train the machine, and okay, which one has offer a best way. You can see a different way of actually different algorithm to train that machine. This paper is already published at IEEE Access. If you want to look into these different algorithms, please welcome to actually look into the signal. Here we look into, again, data rate with and without that equalization. You can see it's failing at very low frequency of low bandwidth. We talk about 4 kilobit per second. You can see the signal is already unable to be recovered. However, within the use of this, you can, in principle, pushing the bandwidth 9 times bigger than itself using this ANN, however, within the limited bandwidth again. Okay, moving forward, dealing with the flickering problem. Okay, just have a look into this. Okay, what we do here, we have a signal. We want to transmit that without the need of having a flickering concept. So how do we tackle this? Okay, we have to say, okay, imagine each symbol will divide into 2 chip size. And the aim is here to equalize the power of this chip. Basically, each symbol has to have a same power level in order to avoid having a flickering. So we divide that chip in the symbol into 2 chips, and it's like, let's say if it is the palm level and using palm modulation in this specific case, if you have the symbol with the intensity of 3, then add another level of stabilization to get 0. If you have 2, this basically have a 2 chip to compensate for each other. So if you have basically that stabilization unit to get almost the same, so you divide, if it's 1, 0, then you will divide that chip into 2 sides, and you will change the way of looking into that symbol in order to have an equalized power in each symbol. I mean, yeah, I'm not able to see it carefully in here, but you can see in here, okay? You have one symbol that This is what we called it CP PAM. It's constant power PAM modulation. So you take a normal signal symbol and you divide that into two smaller chips, and you compensate based on that power of the initial one to have equal average power over that symbol. And therefore you tackle the problem of the flickering. And we call that stabilization level. And this is the way of actually looking into it. Again, this is the system that been set up. You have a symbol that you modulate that using PAM modulation scheme. You design your protocol, transmit the signal, receive that signal, trying to adopt similarly the ANN equalization and look into the problem without having the problem. And this is the system we design. And it has actually the data, no flickering. It send the data with a few kilobit per second bandwidth, I think 24 kilobit per second. So again, here is just to how do we look into the result? We look from a concept of bit error rate, eye diagram, and this is here I'm just showing the image being captured and cluttered to show the inter-symbol interface that being introduced when I'm using that camera. You can see moving transmitted from 200 Hz up to 1.5 kilohertz. The data units, you can see the recovery of that signal is impossible without the equalization. However, within the use of equalization, you can see we are able to actually recover the signal, and here is the maintaining that the data rate required. So yes, we did look into this, we established this, we look in the results from eye diagram, linearity and error rate performance point of view. And again, the paper here is published and you can access that online. Okay, getting it from this to this one. And if you notice, you have 1, 2, 3, 4, 5 layers. In principle, we have 4 PAM, yeah? PAM is 4 level, but here you will see 5 because we designed actually the header in order to look in the beginning of that symbol with another level, and that we used for utilizing the signal and recovering it. Okay, this is from data communication point of view. Okay, moving forward, another application for that camera from localization point of view. Okay, again, from a concept of having the use of this camera for localization, mainly for indoor. I guess here from a tunnel point of view, we heard a lot about Chile and the use of that in here. Okay, camera can be utilized for that from advertising. This is, I put a multimedia from my previous project that we worked with Fari and another company based in the US. I guess we developed a system where you actually trying to, for localization, mainly for maybe can be for advertisement of some application. You can see that camera can look into things, position the things, and using this for some certain purposes. Okay, this is the website of that company anyway. So from that concept, moving to the, let's look into, okay, what we can do from a localization point of view. I will brief here of, okay, what we have done from a localization. So using a single light, we say, okay, using a single light that been sent on a camera receiver, you could in principle work out the position and telling you where you are in that based on a specific algorithm that you can develop. So here is our scenario that we put forward for that. Again, you have a light source sending its ID, and the ID is modulated and sending it through a light source, flicker-free light source for sure. Again, the signal is being received in here. You get a camera, and we did some processing in here in order basically to work out the position of that light source in the image and working out the position out of that. I will not go in depth into this, but we'll see the following slide a little bit of these details of how did we mention this. Here is the system parameter that been adopted from a current bias current that been used for the lighting the LED. Again, from the camera receiver point of view, what is the parameter of the receiver, then the channel up to basically 2 meters, and then we used how to evaluate the positioning. We use a specific robotic arm with a high resolution in order to be able to measure accurately the positioning. Here is actually the system experimental setup that we've done. You get a camera, the light source sending, we move that along the certain basically room size in indoor with some certain exposure. And you can see here we test different exposure time, and in order to detect in the camera basically that light source and what is that from term of accuracy, how accurate is this locating that. So this is a photograph of the setup. Moving forward, different exposure. You can see from having a light source like this captured in a camera to having intensity one and a blooming impact that actually impact the accuracy of that signal. And here is, if you take that one and we just look at it carefully and saying, okay, what is the minimum, what is the maximum for a different one? You can see this is a rainbow just to show the procedural increment of that exposure over time, basically. And here is the detection of that light source from a different exposure. And we looked into something called peak signal to noise ratio, is the pixel signal to noise ratio based in transmitted receive one, and find the difference. Again, this paper is already published and you can find the source in here. Yeah, here is another technique that we used in order to tackle that problem of having these different exposure and a blooming impact. Okay, if I'm using a small impact, I can locate the source. If I have a high power exposure for the camera, you can see that location of that source in the image. It might be a bit of difficult way. So we introduced something called mask generation, and it's just like, okay, detect that initial size or radius of that one and generate a one, and then do multiplication between both of them, and then give me the signal. And let's look into what difference in terms of exposure time. And you can see here is normalized received one over that pixel. And you can see, you do that way of doing this, so you can actually get the same result of accuracy along the way, and meaning that I'm trying to localize the center of that light based on this technique, and rather than having exposure. So sort of you solve the problem of having different exposure time. Oh, sorry. So I'll go forward in that. Sorry for this. Again, from a localization point of view, this one I will be presenting it in my presentation as a paper that I worked with Vicente. Moving forward okay, I'll just go through it fast. I will not talk about it. Sorry, because I will talk it later, because this, from a physical point of view, security, you can have you can use the camera. You can see a lot of camera used for security purpose, that you have it in everywhere. So you can utilize that to provide a security region. You can have a light source moving forward, and you design a system. Again, if you are interested, we can talk about this later on. And this was a collaboration with NICT. The last bit of this is more about introducing Carlos' work and myself about a single photodiode that you can have from a point of view of having optical receiver and a single photo cell. So we were looking into a photovoltaic. It says, can we use this as a receiver? Can we capture that? And having a self-powered receiver that can actually capture the signal, as well as providing basically energy harvesting without the need of power source. And this is one of the samples that we actually gather from in collaboration with the Finland Institute and Oxford. They fabricate the samples for us, and we use a material called perovskite, and that has an ability to self-powered, and it provides basically more efficient than silicon. This is a very new result of the work. It offers a wide absorption and offer flexibility as compared with normal photodiode. This is from a design point of view. We will see that work about from a communication point of view. So we took that sample, trying to actually look at it from a point of view, can we use that as an optical receiver? And if we, how do we actually characterize it? So here is it. I'm just going very fast about this. Okay, as simple as that, looking into this, that perovskite material, it has three different actually elements from the perovskite material. And from a chemical point of view, we get the electron and hole transport layer. We use some basically different materials for design than being actually suggested to be used, some of them to allow the transport layer for electron to having a fast transportation for that electron, and delivery for the again for the holes. Here is like the electrode. In order to have a high conductive electrode, you use the gold for that. You can see with because it has a higher conductivity and excellent conductivity. So looking from this point of view, we assemble the assembled one. We look from energy and communication characteristics. I mean, the characterization from optical point of view will later on, just after me, Carlos will present that to some level. And before I actually conclude here, I'm just getting this opportunity to play this multimedia for the other project that we work with in Northumbria. And that was basically trying to establish the use of optics in the space. If you are, please, can you open that multimedia for a 2 seconds? If you can you play the multimedia, and this is just to show a brief introduction, then we can conclude. So this is one of the latest work that we are doing at the moment. So basically designing that CubeSat for the use of space. The project was funded by the UK Space Agency, and this is so the aim is to actually create a communication between inter-satellite communication link in the space. Here you can see with some certain distance with 1,000 kilometer, with some collaboration with the different universities and around in the UK basically, and then with the companies trying to design that one. So basically we started the optic communication here from a computer point of view, also at a company leading for the computational power of that one. In Northumbria, we're trying to establish the optics links, as well as we have a team for the solar cell. Here is with the Durham, they're trying to design the optics that been enables for us to do for a communication point of view. So we talk about the aim is to having gigabit per second data communication and creating an inter-satellite optical link between two of them. And this is a simple video that actually developed for a marketing point of view, and just to show the concept. Again, if I'm just moving to summarize from that point of view, trying to have 6 CubeSat, basically very small one, INTES, and having high data rate. And basically this is where sit in based on whatever exists in the literature. And here is the head or optical, the initial design that we worked out. And yeah, I will be further in this work. We are currently working on that, and hopefully we'll reach somewhere and report the result eventually after this. So again, just to summarize the work for OCIG, because I'm a part of the optical wireless, as I said initially, I just put some of the word and what has been developed by, actually led by Fari. You can see him in here and here as well. And here is some of the work of the camera that we look. Here is for a communication that previously, and this is my colleague Shishang again developing this. And this is the CubeSat, the previous one, initial demonstration in the lab for that one. I mean, to conclude the things, okay, this is what we looked at. We looked at the OCC as a way of communication and compared that from VLC. And basically, this is the funding that OCIG and FARI has obtained over the years. And I'm actually glad to be working as a part of it, as well as the new that. And here is the thankful for everyone who listening here. And I'm happy to actually, and sorry for the latency, and I'm happy to have any question and anyone have any concern in that regard. Thank you.
Thank you, Osman, for your presentation. Very interesting. Questions? Anyone?
Very, very interesting. Yeah,
Thanks,
I really
Ishan.
like your work and also your presentation. Congratulations for achieving all of that. I know it involves a lot of hard work, and I can see from you. Yeah,
Thank you so much, Ishan.
Yeah, so I'm really happy with your progress. And so, Atman, the CubeSat is a very interesting project. So what do you think could be the challenges? Maybe the data rate is okay, you can achieve with commercial lasers. Do you think that, what's the challenge you think that could be?
Okay, thank you, Ijaz, for the question. Actually, very good question. Okay, having a CubeSat and enabling this. Okay, what is the challenges of establishing CubeSat based on optics communication is we look from actually few problem and key point. One of the main key point is actually having the ability to track that signal from acquisition and tracking point of view. So basically having a path model of positioning, acquisition, and tracking is one of the main challenges, where you actually you have two dynamic systems moving independently, and you want to locate one source to another, and basically trying to find find the area and in which that you exist, and then look into a very small and tiny, we talk about few micron, like 20 or 100 micron photodiode or photodetector. And this is one of the key challenges for enable such a system. And for the knowledge of people, there is no existing path in the space at the moment in the planet at all. So one of the key challenges for this project is having a path system, basically locating that light that being transmit to the receiver. And another key challenge, actually having the data communication, it's also very challenging regardless of the laser, because the fact that you end up you want to have a smaller system with an optics that have been designed to transmit that signal, and again, it has to have a high speed and low latency, and having the optics that can survive in the space is another different problem. And third of all, actually having the problem to deal with the space. Once you go to the space, everything changes, because the fact that you have to look into temperature point of view, a different characteristics altogether. You want to survive for long, you want to survive a high temperature, low temperature, and you want to be as power efficient as possible because you want to last long. So you have to come up with a solution for this. This is a very new to me and very challenging. I mean, I'm always trying to refer to Pari and people from physics to help us with this. I mean, we have now a new lab that even Pari and Eamon and then Robert Weeks is as well, like they started and trying to basically moving the direction towards that, because it's a growing industry. You can see a lot of big companies now trying to do such a things. And I mean, SpaceX, for example.
So I've been looking on satellite communication toolbox on MATLAB yesterday.
Yes.
It's for radio communications, but I think it's very paramount that you simulate your system really, because once you're in the space, so maybe my question is, are you simulating? Is there any platform you can use to simulate?
Yes, I mean, having to simulate the system is also another challenging factor to establish high power intensity, and you want to be having a reliable one. So yes, we are trying to work out, we have a plan to do a testing, and basically we have from a simulating point of view, we did already budget analysis in MATLAB and so on. But from an implementation point of view, you have a totally different domain. You come up, we have a lot of support from industry and trying to solve that problem, but having this is again a challenging thing to look at.
Thank you so much.
You're welcome. I just hope to have that list.
More questions? Okay.
Thank you. I enjoy your presentation. Many different ideas.
You're welcome. Thanks.
It's hard to follow all of them. I enjoy it very much. So I have a question regarding, this is the first time I read a few things about camera communications. But I find it very interesting, and many challenges you need to find and solve. Regarding the pointing of the camera from a mobile phone, is that an issue? Is something that you take into account for the test you've done so far?
Yes, thank you for the question. So looking into the camera point of view, so what we deal is we have what's so-called field of view, which is the angle in which the camera can actually have access to. It's like the example of yesterday, Fari was mentioning, okay, and if I'm in a room and I'm opening my camera, how many light source will I see? Basically, it depends on the field of view of that camera. Changing that field of view will change the amount of data captured per frame. You know, imagine have a picture or a frame, and if I'm decreasing that field of view, I'm actually changing the data rate. I'm changing the amount of data being transmitted and received per a single frame. And therefore, yes, it does play a role. And we have actually worked out an equation. Is already, if you look into literature, you will find it. And basically, okay, in increasing that will have some certain amount of impact in terms of how much data I can send per a single frame, and therefore for a multiple frame, and then eventually working out the bandwidth or data rate. Thank you. I hope that it addressed your question.
And I have one more question, if that's all right.
Yes, sure.
Obviously, the data rate is limited, and you would like to find some way of increasing the dimensionality of the data you see. But you have your camera has just an intensity. So is there any chance that we could build now a camera phones cameras that have sensitivity for polarization.
Mm.
Maintaining intensity, but if we added polarization, then maybe we could have some extra dimensionality for it.
I think this is a very good question as well. I mean, there are actually some of the people who looked into having a camera in which that array, that pixel array, one of them used for visionary and the other for the data, in which you provide that high data rate. And this was reported in Japan, and they have achieved around 100 meg based on initial design. But okay, why I'm looking here from a different perspective is because we are trying to access whatever existence in literature. So I mean, looking from that perspective, I think is very futuristic and it's very nice. And I think probably, yes, it depends on this manufacturer of these CMOS cameras, and maybe they come up with this and they adopt that scenario, and in which you have both of them and you will enable higher speed. But yeah, that's my answer for that. Thank you.
More questions?
Okay, thank you. Congratulations for your presentations.
Thank you.
I didn't see it at all, but I would like to know if it is possible for you to provide us a little bit more details on the advantage on perovskite, not only regarding to bandwidth enhancement, but also in terms of energy harvesting.
Okay, so thank you for the question. A very nice question again. For that, from an energy harvesting point of view, because we characterized that one as a part of one of the paper that Carlos was leading and myself as a part of it. We looked into this characterization from a PV point of view, from energy harvesting, and we measured efficiency for that one. And I didn't want to get into details because right after me, he will go and in the stage and he will show you exactly what you were asking for, and hopefully will address your concern from that point of view. I hope that's okay for you. Yeah.
That's okay. It's okay.
Thank you very much.
You're welcome. Thanks all. And thank you.
Now we start with session 3. It will be chaired by Vicente Matos.
Hello. Good morning, everybody. Thank you, Osman, for your presentation. We move on to the session 3, in which we'll give each presenter 15 minutes. We start with Lidices Reyes-Hung with crop stress detection with multispectral imaging using artificial intelligence. The floor is yours.
Good morning. The title of my presentation is Crop Stress Detection with Multispectral Imaging using AI. I am Lidice Reyes-Hung. I will start with a short introduction. Then I will present our proposal, followed by experiment result, and finally the conclusion. The main goal is to detect stress in crops from the multispectral images taken by a drone. Stress can be pest, lack of water, and other. On the left, we can see a multispectral image, and on the right, the same image labeled with stress in red and the healthy in green. This is a proposal for a system diagram that consists of 4 parts. The first uses a drone with a multispectral camera to capture crop data. Then a Starlink antenna is used to transmit this data in a place where there is no internet coverage. The link transports the data via satellite. the processing, analyzing with AI. And the panel show the information to customers. In the diagram, show the flow to detect stress in crops using multispectral imaging. The processing consists of obtaining, pre-processing, and analyzing the image captured by a drone, separating the crop from the background and detecting stress with vegetation indices. To analyze the images obtained by a drone, it is necessary to create an orthomosaic that is a continuous, homogeneous, and rectified image of the crop. IsoMetaChef helps correct and combine our aerial images at the same scale and their orientation, and export the select polygon of each orthomosaic to obtain an exact representation of the crop area of interest. Vegetation indices are measured used to evaluate the health and the density of the vegetation. They are calculated by combining bands of the multispectral images. The image shows NDVI, one of the most used that uses the red and the NIR bands. Image segmentation is key to separate the crop from the background using algorithms like thresholding or machine learning. On the left, we can see the Otsun method which selects the optimal threshold by maximizing the variance between classes. On the right, we can see the K-mean method, which is a clustering algorithm that divides the data into K clustering, minimizing the distance between the data and the clustering center. We can see the result of Otsu and K-means. You can see that Otsu has some problems, while K-mean is almost perfect. From the calculation of the NDVI, we can identify healthy and stressed crops. Then an operation is performed between each result and the segmentation crops. Obtaining is stressed and the healthy part of the crop of interest. On the right, the healthy crop in the show is green and the stressed crop in show in red. We evaluate the quality of the segmentation using the inner sum of the square, Davis Baldwin Index, and Kaliskine-Ballas Index matrix, getting better result for K-mean. As a conclusion, we explored stress detection in sugarcane cultivation using machine learning techniques. We proposed an internet and satellite based monitoring system to evaluate the health of crops. We compared the effectiveness of different crop detection methods, also and K-mean. Thank you very much.
Thank you, Lidices, for the presentation. Do we have any questions from the audience? No? Perhaps I can ask something because I also had experience working with infrared light. I believe you're using infrared spectrum in your measurements. So
No hablo inglés.
no, ¿puedo preguntar en español?
Sí, ahí.
La cámara multiespectral trabaja también en el rango infrarrojo, ¿no?
Sí, la
Ya.
cámara multiespectral trabaja en el rango visible
Ujú.
y en el rango infrarrojo. Tiene infrarrojo cercano, sí, sí.
Sí.
¿Qué más?
Como sugerencia, creo que se puede ver el estado de salud y una posible extensión del trabajo podría ser el estado de madurez de la fruta, que fue un trabajo que hice en la Universidad Católica con mi práctica, y ahí usábamos near infrared para el estado de madurez de la fruta, que podría ser un nuevo
En este trabajo futuro voy a trabajar con un dataset de papa, de cultivo de papa, que tiene etiquetadas imágenes, las imágenes, cultivo, qué parte está estresada y qué parte está saludable. Para detección de objetos de deep learning. Entonces lo que voy a hacer es trabajarlo de otra forma y poder hacer eso. Ese es mi trabajo futuro aparte de esto.
Thank you, Ulises. We can move on to the next presentation. In this case, we have paper from work in Czech Republic and Canary Islands. Presented by Clara Eolos Jarosikova. It's called Pilot Experiments of Side-Emitting Fiber-Based Camera Communication for Wearable Applications.
Okay.
Floor is
Thank you,
yours.
Vicente, for the introduction. Okay, yeah. So the general concept of OCC was already introduced. Well, it's well known, as it was also introduced to by Othman today. So we can look into the side-emitting fiber part of this setup. First, what are those side-emitting fibers? Well, those are fibers that are specially designed to emit light gradually, where in regular standard optical fibers, the goal is to transmit as much of the light which is coupled at point A to point B. Side-emitting fibers are designed to gradually emit the fiber which is, the light that is coupled over a defined length, which is usually about 1 meter. To achieve this, usually some kind of nanovoids or particles are introduced into the fiber's core or cladding. This results into the side emission of the light. Okay, so when we want to combine the side emitting fibers to OCC, first we need to couple the light using LED. But this adds another complication into the system. Why don't we use directly LEDs? Why add another layer? Well, by coupling light into the side-emitting fiber, we basically create a diffuse, distributed light source, which works as a continuous LED stripe. But unlike a continuous LED stripe, we have a radiation pattern of 360 degrees with these fibers. Standard LEDs have about 120 degrees radiation pattern. And also, these fibers are very easy to bend, which opens up new opportunities for applications because we can shape these fibers. Yeah, first, sorry. So we have the transmission part of the setup, which is the side-emitting fiber with LEDs, and the rest is standard OCC with rolling shutter camera capturing the fiber. Now let's have a look what the captured images look like in this general setup. Some examples are in the top left image and bottom right image, with the data represented as dark and bright vertical stripes. After we capture the images, we select a region of interest, and then we process the image. We get an intensity profile, which we then normalize. We perform binarization, and then we can get the data that we transmitted. So this is already standard OCC. Okay, so that was the general side-emitting fiber-based optical camera communication, but the fibers are bendable. Can we attach them on a t-shirt? Let's try it. Okay, so we took a white t-shirt and we sewed it using white thread on a t-shirt. This, on the bottom left image, you can see a close-up of the fiber with the thread. The outer diameter of the fiber was 4 millimeters. We started on the front side of the t-shirt at bottom part, and we went up over the shoulder and to the back, as you can see on the middle photo, creating like U-shape with the fiber. To generate data, we used Arduino Nano. This is because Arduino can be powered by power bank, and we don't need any kind of DC source or a huge waveform generator. With Arduino, we can create very portable setup, which is great for wearable applications. You don't want to carry your generator in hand, right, or in a backpack. So after we generate the data, the wearer with the t-shirt stood in front of the camera, the rolling shutter camera, in distance of 25 to 200 centimeters. And we captured 2 sets of images, front side of the t-shirt and back side. Yeah, here is a close-up with the Arduino Nano LED and 3D printed LED holder, which was developed by Vicente, thank you. The side-emitting fiber as transmitter and rolling shutter camera, which is capturing the images, and Raspberry Pi operating the camera. We used Raspberry Pi camera. And for our experiments, we used 3 modulation frequencies, about 2.6, 3.5, and 5.3 kilohertz. And some of the other. If you are more interested in the parameters, we can look into them more later. It's not that important for now. Okay, so we captured the images. Let's have a look on what our data looks like. This is examples of 3 images. It's for the same frequency, 2.6 kilohertz, in front side of the t-shirt in 3 different distances. And the contrast of these images is a bit increased so that we can see the data better. But in these images, we can see a phenomenon that is very well known for people who work with OCC, but for people who are not as familiar with it, it might be a bit counterintuitive, because here we can see that in each distance, the symbol height is the same. Regardless of the distance, the symbol height remains the same, because how much pixels covers our one bit, one symbol, it's given by the frequency, by exposure time, by other parameters of the camera. So regardless of our distance, we get the same data. Only the width is what's changing. But this is good. We can use this information that each data, each symbol remains in the same rows. We can use it for capturing more interesting shapes. We could create some interesting shape and find the region of interest. And since we know that each line is one symbol, we can simply summarize each line. But this is for future work. For now, let's look at the results of our experiments with this t-shirt. Here are bit error diagrams for front and back section of our experiments. All of our results fall under the forward error correction limit of 3.8 times 10 to minus 3, which is great. We want this. And if you compare the distance with increasing distance, the bit error rate gets worse, which is attributed to the fiber being more narrow in higher distance. We have less data there in the vertical region, no, horizontal. And when we compare the front and back section of our results or the t-shirt, the front section of the t-shirt gives us better results, because now remember, we have our LED coupled on the front section of the t-shirt. So as the light from the fiber is gradually emitted, the further we get from the LED source, from the light source, the lower is the amount of light that we can couple, or not couple, we can capture. So because of this, we get worse results on the backside of the t-shirt because it's further from the light source. Okay. To summarize my presentation, the advantages of using fibers are that it's very flexible and it's possible to shape into many different interesting shapes, yeah. And since these fibers are flexible and lightweight, they don't interfere with wearer's movement, so they can be worn quite comfortably, and it's not as bulky as some LED arrays could be. And from our experiments, we can conclude that the frequencies that we use, 2.6, 3.5, and 5.3 kilohertz, are suitable for this setup up to 2 meters. And in the future work, we would like to have a look on more examples of shapes, more shapes. Maybe some color shifting would be very interesting. And as for now, we were using plastic fibers, but I'm really looking forward on working with silica fibers. So this is what we plan to do. Okay, thank you for your attention.
Thank you, Clara, for your presentation. I'm sure there is a lot of curiosity from the audience. Do we have any questions?
Thank you very much.
Yes.
It's Clara, right? Okay. I'm just curious. Why did you choose your transmission frequency in order of kilohertz? Why?
Well, you think it's too low or too high?
No. It's just to be curious because
Okay.
in all of the presentations, the order of the transmission frequency is 100, 200, but it's higher. So it's just why.
Well, we wanted to achieve a symbol height of the transmitted data of 10, 15, and 20 pixels, like this. This symbol height. And for this reason, we calculated what frequencies we need, and these were the frequencies that were suitable for our camera.
How many do you need them to make variables working?
How many?
One fiber in a cloth is enough, or you need too many?
Well, for now we used one fiber. Well, when you have more fibers, you can transmit more channels. That's right. But for some minimal like identification data or something like this, one fiber should be enough. It's like single LED you transmitting for OCC. But it's a good point. For when you have more fibers, you can have more channels.
Yeah.
Yes.
But the application point of view, you need a source as well in the variable. So this is just if that's low, you pump.
Oh, there's an LED.
Okay.
Yeah.
At the end.
This is the fiber, and here we have an LED.
Yeah.
This is a couple of modulated using Arduino. So yes, we need some light source, but we need only one light source for 1 meter length of the transmitter. Yeah, correct?
Yes, I think you were giving a presentation in a country which has got one of the biggest mining industry, which is copper mine, which most of it is actually underground, although they have open cast, but they go kilometers to underground. So from your point of view, do you think that this technology would be very good in underground mining for the health and safety of the miners?
Could be. Well, it depends on assuming that there is direct. We can the point was called like we can see on the miner there is not too much dust. then it's good. Yeah, it's a very good point. It would be very helpful. Actually, I think now you can buy a backpack which has introduced side emitting fibers in it. So you could stuff some equipment for the miners in it, and they could be visible. It's for safety, and some information like their number, like, or name, some health information could be transmitted using this communication principle. Yeah, that's right.
So therefore, that takes you, the next stage is that.
The line of
if
sight.
it- Yeah, if it's going to be used by miner, because miner must always wear a jacket, safety jacket for visibility. Therefore, this is. So in the lab, what you need is that to create that condition. So you can do the test and see that how far, if for example, something happens, accident happens, how far could the rescue team be able to detect any information coming out of this from the miners who are trapped?
Yeah, well, that's also a good point. In my previous paper, we were measuring how far we can see. We were using different lens. Here we wanted to, for the wearable application, to have wider field of view, so we chose different lens. But for the long distance measurements, we were able to achieve 40-meter distance quite successfully. So this is your answer. We can see them for at least 40 meters. With the use of different lens again, we could see even further.
Okay, we have time for one last question. Tic-tac-toe. I'm sure we can discuss later also.
Just quick question, because I missed this part during the presentation, if you already discussed this. How is motion affecting these communications links? And if motion affects, have you think about a measure to compensate this mobility? I mean, if somebody is wearing this device, but is moving, for example, a miner.
Well, yeah, it's a very good point. Actually, the movement, there are two parts that are crucial. One is to keep the transmitter in the field of view. If someone just steps out, we can't capture them anymore. And for now, we are not considering this type, because there could be some camera movement detection introduced. But for now, we are focused more on the other part, which is looking for the region of interest. For these experiments, we did introduce a bit of movement. The person who was wearing the T-shirt, we made them like mid-letter dance, so so that we could test if this slight movement does affect the experiments. And we were successful even with this movement, because with OCC, even if the fiber is slightly tilted, we can still see the data as long as it's covering the whole field of view, the whole height. We can still get all of the data, but it's true that it can be tricky. Yeah.
Thank you very much, Clara.
Thank you.
And we move on to the next. So next presentation is by Julio Lucero. Paper called "Choosing Sensors for an Underground Mine." Exactly what we said. With FSO employing QGA.
Hello, everyone. I'm José Azócar. I'm going to present this work on behalf of my colleague, Julio Lucero, who had to travel to Colombia to see his family. So this paper is called the Choosing Sensor for an Underground Mine with FSO and employing QGA, which is quantum genetic algorithms.
So here's the content of the presentation. First, I'm going to give a little bit of introduction and context of all this work. Then I'm going to show you the system diagram we are working currently in this and other investigation. A little bit of context of quantum formulation and genetic algorithms, and the Grover's algorithm, which is a particular algorithm that we are working right now. And finally, the results of this work, and then the conclusions. So this work starts with a question: can quantum algorithms be used effectively in underground mining to optimize the operations? So, as you know, you must know, the underground mining operation is a very harsh environment for basically all the systems that are working in that area, especially a telecommunication system. So because all the pollution, we have diffraction of the wavelengths and all that. So our primary motivation for this work is explore the fields of different forms of optimize the resources that are currently using in the mine. That is why we are working with genetic algorithms, and we also are continuing. We are always exploring the different ways to use quantum formulations in different algorithms, but not in the classical way, that's with a quantum computer, but in like an alternative way that we are using the formulations of that are proposed in the quantum computing area, and we are taking that formulation and applying in different algorithms. So we are aiming to combine different technologies, all in the content of smart farming, in this case, smart mining, smart farming, smart everything. So, and this a little more context of this work, but because this work is aiming to optimize the resource of specific of sensors and different devices inside the environment. We are using quantum genetic algorithms to optimize a certain target function. In this particular work, that target function is an derivative of the avalanche property of cryptographic algorithms. This is important because, well, my main line of research are cryptographic systems to generate secure keys. Yeah. So if we are generating one key for each device presented in the system, maybe if we have only 1 or 2 or 10 devices, it's not a big problem. But what if we have 1,000 or 10,000 of devices? We need to optimize all these the resources with all as much as we can. So this is the system, the diagram we are using right now. In the first block, we have all the sensors, all the gas sensors, the temperature, the humidity, air flow. We also have the telecommunication system that are probably in the edge. We have a different experience with using LoRa, using Jetson Nano with 5G in this case. That is all the technologies that are in the edge. Then we are transmitting all the different variables such as humidity, temperature, and also variables of the network itself, like SNR and RSSI, and that we all combine all this information in only one package and send them to a main, like a concentrator. In that concentrator, we are that is the second block. In that block, in this work, we are currently using doing different tests of the algorithms that we are showing today to optimize, to choose one of all the sensors or groups of sensors and choose one, and that sensor is the representative of the the vicinity in which these sensors are placed, and then this decision of the sensor or not, we transmit that to the main center of control room. In that point, we have the IFSO laser, which is why it's in detail. So here's a little introduction to what is a qubit. Basically, a qubit is a particle that we can use to represent different states, and difference to the classical bit that is only one or only zero. We can represent the different things with only one particle that can be represented as a linear combination of the probabilities of this particle being zero plus the probability of this particle being one. This is all very summarized for that. And the genetic algorithm, well, a little reminding of how we work our genetic algorithm. Starts with a different population, a population with different chromosomes. These chromosomes represent different properties of the population. Yep. Then we evaluate the population for this target function. In this case, we are using this that represent the avalanche effect where we are working in this particular work. So then we have, here's an image. So these are two individuals of the populations, and the different operation of the genetic algorithms that we're using are the classical ones, the crossover, the mutation, and the selection. We select two parents of the different individuals, then we cross interchange his properties, and doing that, we generate new possibilities with different properties into the next generation. This new population may or may not be better than the previous one. That is why we have here this block that is this population, but works as we are expected. And the Grover's algorithm is one of the many quantum algorithms. This particular one allowed us to search more quickly in an unsorted database. Yeah, and then we are looking for a specific value in a huge set of data, and this data must be in the proper form and format. We are working with quantum formulation. But if we do this correctly and we then apply the Weber's algorithm to search our optimal value, that search in the database is take very less time if we are doing the traditional way. So these two results, if we combine these different techniques and different techniques and algorithms, we can represent different sensors or group of sensors. In this case, we are using in gas sensor and temperature sensors to represent different spaces on the, where it's located in different spaces of our tunnel. And then the data that these sensors generate that that are sent to the control room, yeah, this data is encrypted, and then to this packet of data encrypted, we are calculating the fitness of the algorithm. So here we have two tables with different different fitness. In this table here, we are using a classical genetic algorithm to prove if we can obtain a better fitness than the quantum genetic algorithm. So you can see here that the fitness that we are obtaining with the classical algorithm and the fitness we are obtaining with the quantum genetic algorithm, the QGI is winning in the fitness the test. So this table is represented here. In red is the classical genetic algorithm, and in black is the result of the quantum genetic algorithms. We have here the different generations of the genetic algorithm per se. And here the fitness obtained through that process. In average, in all cases, the quantum genetic algorithm wins to the classical genetic algorithms. And well, that's finally to conclude. We clearly observe difference performance in the capacity between the classical and the quantum genetic algorithms. Yeah. So, however, our main point must beyond that see that the quantum genetic algorithm wins to the classical is continue to explore different ways to use these new technologies and see if they are capable to contribute to the quality of the communications and interior of mining. That's it for me. That's all for us. Thank you.
Thank you, Jose, for the presentation. Do we have any questions from the audience? Perhaps I can ask. I know it's very difficult to test these systems in a real mine.
Yeah.
But how difficult it is, and if it's so difficult, are you planning on building some kind of setup in a lab that helps you emulate these conditions?
Yeah. Well, we in the lab we actually go to a mine, a school mine. It's not an operating mine. It's for learning. It's for doing the experiment. Well, the FSO system works without any major problems. We do tests with and without pollutions, and we were able to send the data from the interior of the mine to in that opportunity or else control center that was a box with a computer. And in the lab, we also have how do you say maqueta? A mock-up of a tunnel with different sensors. We are currently transmitting information from this sensor through MQTT to our data center.
Do you have any other questions? From Carlos.
Sorry, but I didn't see the connection between these quantum genetic algorithms and the undermining, well, the mining application. So, how is it related in for your work?
For this work,
if we change the environment, we go to another place. What will be different?
well, in this work, most of the work in here in Chile, we are mining country. We are focused on mejorar, improve our telecommunication systems inside the mining. That is the initial reason of the why we are focusing in underground mining. But you're right. This concept or this work can be applied on other fields. In fact, we are working with smart. We have a project in smart farming that we are currently also doing tests with this work.
He's asking about what are you improving
With
the genetic with the quantum optimization algorithms? Why are you improving?
We in simple terms, we are using less resources to monitoring the inside of the tunnel. That's
just for the identification of the sensor. I mean, you're using these quantum genetic algorithms for coding the ID of the sensor, or because that's the part that.
Can you repeat, please?
Yes. You're using the algorithm just as a way to more rapidly identify each sensor, or what's the?
We in this work we are using the algorithm to identify the most secure sensor. That is because we are using the target function to calculate the limit. This function to represent the avalanche effect. So we are currently aiming to, in this particular work, to select the most secure and reliable sensor and information that is inside the domain.
Okay, thank you, Jose, for your presentation. We move on to the next one. Second last by Cristóbal Carreño, called Recovery Strategy. Welcome, Cristóbal. The floor is yours.
Buenos días a todos, a todas. Bonjour à tous. Welcome to everyone and good morning. Today I'm going to present you, or it's a part of my PhD with my two supervisors. It's a recovery strategy for building a resilient BLP system. It's rated with Osman or with Muhammad, I think. It's a grand lab in the group of autonomous and resilient networks at Nancy, France, at the Université de Lorraine. So the content, it's quietly, we are skimming a lot of things. So if you have a question, feel free to ask me at the end of the presentation. So we are starting with resilience concept and robustness dilemma. Why? Because when you think about a person is robust, you think it's a lot of muscles, a lot of strength, right? And when you think a person is resilient, you think that we can overcome everything it's passing by through the time, okay? So there are two different concepts. So when a person is resilient, maybe you can think, oh, that person can overcome everything, but it's not that the same way. It's the same that robustness, you can resist. You are designed for resist, okay? You are static because the design you make once, And you can obviously improve it, but it's obviously remain at the design stage. And you will know all the perturbations. That's a big one thing. And resilience on the other side, in the AYUV, it states that the resilience concept arises from rebound from one perturbation, or it's a robustness property. Okay, but Clement et al., it's a publication in France that states that now the resilience property comes with the ability to recover and at the same time the ability to adapt from all the perturbations. That leads us to a dynamic concept, and it's not always in this design stage. It can evolve, okay? And all the perturbations are not well known. That's the big difference in resilience and robustness. And this is our conception of resilience. You can see at the green line, okay? It's applied at positioning systems. And in max, it's the max error at positioning, okay? So the green line shows that it's a robust behavior. Why? Because it remains in a certain level or on a certain level. You can fluctuate, you can go up, go down, but you remain at the safe or your desired state. And the red line, in contrast, it can go out my desired state. That is different. So if an event happened or a perturbation happened, and in T2 we go out, so my performance is degraded, and we have to apply a certain recovery strategy. That's the title we are talking about. And after that, we apply our recovery strategy. We go down, we go. It depends of the slope, but we can return of our desired or maximum state or tolerable state. Okay, that's the big difference. Okay, so you can realize it's a spoil, but you can realize that recovery strategy plays a cornerstone, a big role in the difference of robustness and resilience concept. So we move out with this concept in mind, the BLP systems, and what is the problem statement. Okay, that is our platform in France. It comes with 9 lights, okay, that mounted in a ceiling with bars. It's a height of 3 meters, I think, and it's separated by a square room of 3 by 3 meters square. And each light is sending a square wave with a certain frequency. Okay, you can see all the diagram here. If you want to get more detail, we can ask later. So this pattern was developed by Fabien Seguel, the last PhD student. He was working on just robustness, how to transform our BLP systems in more robust. Robust why? Robust, for example, using range-free algorithms. Okay, so what is the contribution of this work? The contribution is extend the use of resilient concept, right? And taking beyond this robustness. So we start with the robustness concept at the work of Fabian, and we're moving forward to the concept of restoring the system functionality under certain perturbations, okay? Or obviously in performance degradation. But the thing here is the loss of service, the positioning service. Okay, this is the true iteration. This it's very, very known in literature. Okay, we have a distance estimated by the RSS, the receive strange, and here is true iteration. It's a geometric relation when the light is projected by circles on the floor. And here is the optimization problem. When can we solve to obtain the coordinates of our PD or camera or whatever you want. So what is the statement here? What is the problem here? The problem here is the iteration, or all VLP and VLC are susceptible to optical power changes. So if we lose the line of sight, if we change the PD of camera orientation, the situation changes and changes a lot. It's quite different from communication system because you can recover some kind of information, but in the positioning system that can lead a lot of huge error. I mean, you can pass from 1 centimeter to 1 meter if you change, for example, the angle. Okay, and here are some literature just to remind that there are some people, some actors, some researchers that are trying to solve these problems, but from the perspective from robustness. That means they are trying to solve one perturbation at a time, okay, in certain and specific conditions. Okay, it's not for adapting, it's not for recovering, it's just to resist. Okay. So here we are proposing a test scenario to test when we can find a loss of service, positioning service, not communication, just positioning. Okay. So it's a circular trajectory. Here we started with a normal scenario, all LEDs ultimately are functioning. After that, we pass a loss of service. We shut down the TX6, TX8, and TX9. Okay, the true iteration doesn't work there. And after that, we pass change a little bit the powers that transmit for the LEDs. So the idea is to switch from a condition when the error it's high or it's increasing. With this in mind, we're moving on to the resilience works that introduce the concept of the resilience concept introduced by IPS system. IPS means interpositioning system. It's more general than BLP, but there's no it works on resilient systems on BLP at the date. I know. So there are 3 of them. You can see that fusion 2 technologies, it's a way to get a kind of level of resilience. Yeah, the Park and Myung use this term, but it's not certainly a resilient systems. Why not? Because they do not include the terms of adaptation and recovery. Okay. Here, yes, they include the term, but also they switch. It's different from fusion. Fusion is just to improve, but switching, it's when they consider all the cases when the position is lost and they switch between one technology to another to recover the situation. And here is the same. It's a military application because they use GPS for outdoor environments and IMU or inertial measurement unit for indoor environments. So the idea is to deliver a continuous service of positioning. So this can lead us think, okay, they are thinking in the term of recovery and adapt, but it's more close to recovery. So some remarks here. In robustness, the studies don't deal with the loss of service. They deal with the loss of performance, not service. And that's a quite thing. It's a big thing. So fusion technology provide robustness? Yeah, a lot. And perturbations always are well known. But after that, recovery and adaptation, we have to consider. And I think it's repeated, it's the slide, right? No? I think. So I'm just skipping. So what is our strategy? We are started with a traditional BLP with true iteration method. So we started with the PD. We are choosing PD. We can discuss with Otman if PD is better than cameras. the TI, the bandpass filter, because in the lab we are using frequency multiplexing modulation. So we are separated by frequency, not by time. And we apply the EFT to extract the power, the RSS, via the Parseval's theorem. And after that, we construct a fitting function of the distance versus the power received, so we can estimate the distance. So that is the stage of calibration process. And after that, we can apply the equation of true iteration. So that's normal, that's right, that works very well. But what happens if we, I don't know, we don't receive two lights, two lamp sites? So this won't work. The idea is to, or when we propose this to the observer, what it's going to happen, what is happening. And we develop two, or we take two observers. It's not observer like control theory. This is a different thing. Here is just observing what is happening with the standard deviation of the RSS we are receiving. What is the number of lights are connected, because there are links between the PD and different lights. So we store that indexes. So we have information. What is the difference between all the power we are receiving, and the receiving power leads to, obviously, how many lights are connected. With this information, we can decide in the recovery strategy, obviously due to these indexes, what we're going to do. So if we want, or if we have the efficient number of lights, it means that the connections are established, but the level of the power received is not high. It's a little bit changing. Okay, so we can establish the communication, but we can not perform the true iteration because we are going to enter an error. So in this case, we can switch, right? We can switch at this one. And the other one, we can switch if the lights are inefficient, if are less than 3, we cannot perform that. And the standard deviation is less than the threshold. That means we are not capable to perform the true iteration, but at the same time, we can not establish a communication, or at least just a few. We switch to the centroid method. So what is the thing here? That we can switch between two methods. That's a different way. For example, here we have true iteration, and here we have a centroid. It's a more robust to the characteristics of the signal. That means that we don't need that. We just need the communication links. But what happens if the lights are not efficient, they are not sufficient? Here, we switch to the IMO thing, or the extra sensor. All of them, we can store it, the position at the recovery position, and we can replace the position delivered by the true iteration just for the recovery. That I think this flowchart could be a little bit confusing. I will be more detailed here. So here we have the trajectory. In that part, we have the first scenario. So everything is going well. But after that, we shut down the lights on 9, 8, and 6. So this coverage area, it's not sufficient to deliver or to perform true iteration. Okay, there's no communication because there are no links. So we have to change our technology from visible light to inertial sensor. That's the idea. So here we can appreciate that there's a little bit approximation, but here IMU it's capable to recover the situation. but it doesn't deliver the same approximation or the same error that true iteration. Okay. After that, we have just the variation of the power received, and after we apply centroid algorithm. Yeah, here it's not the same that here in the ideal case, but we can maintain the positioning service. That's the good one. Yeah, something could say, Cristobal, it's not the same error. Yeah, but it's better. You can maintain the service instead of a huge error, because you have to receive some reference when you use the GPS. It's the same way. Okay. Here it's more simple to understand, because here we can let me just remind something. That part is important. This is the recovery. So here we can realize that is the same in both parts. So here we enter to the scenario 2. In a couple of samples, yeah, the algorithm is trying to switch. Okay, so there's a time to take to apply the recovery strategy. So we take some samples, and after that, okay, we switch and we recover the position. That's with IMO. And in the other scenario, in the 3 scenario, when the power are changing, yeah, but for the true iteration algorithm, it's a little bit confusing, but we can still apply because the communication it's working. So the error, it's not the same, but the communication service is established, or the positioning service is established. So in the bottom, you can see the standard deviation of the lights. Okay, and here the number of the lights that are connected. So in this part, you can see that there's no lights connected. That's the reason, because we switch from true iteration to IMO. So in conclusion, I'm not going to make the conclusion classic that we have these results, we have got that numbers. No, we are do a different way, in my suggestion of my supervisors, obviously. The recovery strategy is based on switching technology, but also switching the method. So we can use both methods at a time, but not only the method to improve our error or reduce our error. It's just to improve or guarantee the positioning service. It's a first step to address the resilience concept to VLP systems. The notion of service is also important, very, very important. Why? Because it can deliver the ability to what's happening, what's going on. It's an angular term. So in order to enable the recovery strategy, we have to develop and improve that one. The recovery strategy also must not, it's only for return, okay? We can also address the possibility to make more robust. So robust, it's insightful. It's a kind of level of resilience, okay? And the more recovery strategies we count, and more adaptive will be our system. So this is a very, very important thing. As the future works, we pretend to extend this work with the development of the observer recovery, observer and recovery block, and that's set in a real scenario, that what you saw in the slide, and addressing all of perturbation, for example, multipath or PD orientation or something like that. Okay, so thank you very much. If you have questions, feel free to make it.
Thank you, Cristobal, for your presentation.
Thank you.
Unfortunately, we don't have much time for the last presentation. How many questions do we have? We have one. Okay, we will concede this only question and we will move on to the next one. Ari.
Thank you very much for your presentation. I like your idea of the way you approached
the problem of positioning.
It was not my idea. It
But-
was from my supervisor. Yeah.
Okay, I like the idea regardless of which direction it came from, okay, either whether it's line of sight or reflection, doesn't matter. And I think the idea of robustness and resilience, and I thought you're going to lead me into two-state solution. And therefore you're going to use the knowledge that we have from solving state-based problem. So therefore the robustness become the base, the resilience is the away from the reality, and then you're drawing into the robustness by considering many sub-states around the resilience. And I was thinking that this is how you're going to eventually lead that. But I think I like this idea, the way you looked at the positioning from these two angles, you know, robustness and resilience and so on. And I've got a couple of sort of comments, a question maybe. In an indoor environment, yeah, like this one, what are the probability that n number of transmitters will not be available? In other words, looking at from practical point of view, yes,
yeah,
we can understand that the problem of either partial blocking or shadowing or total blocking and so on. But for things to completely, basically light to go off, it means that physically something is happening. Is that what you're considering when you say that you consider transmitter 6, 8, 9 basically completely not available? Is it because the light is gone? Or is it something causing that within the channel, and therefore you're interested to consider that scenario, and therefore you want to use your method of switching over,
yeah,
and then get back to your reference level, let's say your base level.
yeah. Our first idea, it came from what happened when you block with your body. For example, when you are at your phone and you're walking around, and you, I don't know, turn, you're blocking a lot.
Okay.
That's the first one. And after that, we realized that what happened in a fire event.
Okay.
So in a fire event, you lose maybe all the lights. Not, but the lights are turning off or shut down. It's a smoke.
Yes.
So the smoke can lead you. You can lose all your line of sight, and you can lose your positioning service. And in a fire event, the positioning, it's a crucial thing. You have to go, or you have to know where to go, or the safe path.
But yeah, that's a very interesting point, if you allow me to. Because in terms of emergency, I'm just looking at the district. Suppose that there is emergency here, and we need to evacuate this. So I'm expecting to see some exit, says fire exit. Now these fire exits are no more passive, they're active, they are light. So that fire exit light, if I point my camera, it will tell me that you have to go, because that is not run by the mains, they are run on batteries and so on, they're very protected. Do you think that sort of things could be incorporated into your system to make it more resilient? That I can, if this light fails, I can just point to that, it's tell me that you need to go straight towards that and exit. Do you think that sort of could be included part of your model?
Yeah. The idea also it's to consider all technologies,
Yes.
not just, for example, inertial sensors, cameras also could be a good one, ultra wideband could be a good one, lasers could be a good one. It depends. So the idea is to extend the notion that the light is the unique source of positioning. That it's a good one, yeah. But what happened? It's very weak in certain scenario. So the idea is to work together to become more flexible, become more adaptable. So that's a kind of spoiler of the next part of my thesis. But the idea is to get in levels. We are developing a framework that starts with robustness and that goes up with a recovery stage. And the third part, at the top of the height, it's the learning part.
Yes. My final comment, just this technicality. Do you really distinguish between adaptability and resilience?
It's
Or
a very,
do you
it's
do you
very
think-
hard. It's very hard.
Or do you think they are the same?
It's not the same because you can be adaptable, but not always you can obtain whatever you want. You know what I mean? For example, you can adapt but suffer a lot. It could be you passing through a lot of hard things. So it could be, or it doesn't mean that your targets it's accomplished. The idea of resilience is to pass through hard things, in my opinion, adapt, but arrive to a desired state. That desired state can change, but arrive at least.
Thank you.
So we move on to the last presentation of this session with Luis Soto, I believe. He will give us presentation on optimization of the signal reconstruction process by multi-resolution analysis for a signal with Gaussian noise using the Sure-Shrink algorithm and wavelength domages. If I say right.
Good morning, everyone. This presentation is divided in these principal topics. I will show you the key mathematical tools, the key elements, like a signal with noise, optimization process, the matrix, the threshold, and optimization vector. The optimization process and the optimization reconstruction process, result and conclusion. To start in, the Weber transform is the key tool for work this paper. It's a mathematical tool to allow a non-stationary signal because it simultaneously provides temporal and spectral information about them. A way to type in the Weber transform is multi-resolution analysis, or MRI, which describe a Weber transform as a process that represents function difference level of approximation, which serves to analyze specific parameters in frequency slice according to the needs of a specific analysis recognition. In the figure 1, you can see the characteristic of the WT, with that in the time resolution increase. If we increase the resolution in time, we decrease the resolution in frequency. And you can see in the figure 2, the sweeping, the original signal, using the scale and the oscillation for they're adjusting the frequency to resolution to figure 1. Another characteristic of Weber transform, unlike the Fourier transform, is that the presentation of the input signal is based to use the sinusoidal function, sines and cosines, whereas in the later of the WT, use a group of function called mother wavelets, like wavelet Hart, Debussy, or Koiflet, Seamless, or among others. Therefore, they use a wavelet transform to the performance associated with the analysis of given input signal depend on the mother wavelets. Example of the use of wavelets WT with the MRI is how to process to reduce the noise represented in the signal. The figure 3 represents the difference between the WT and the TF, or Fourier transform. And the figure 4 is an example of the Weber mother, like Debussy's in order to. Another example of the family of the wavelet Debussy's that you can see is the is that represent from the 0 of 10. Should be noted the damages in order 0 resemble the hard wavelet. A simple way to describe multi-resolution analysis is compared to the filter bank. This is a filter bank is a basis on generated bypass filter where each frequency subband represents a unique portion of the original signal in order to separate signals into the multiple components. The discrete wavelet transfer allowed to design and apply of more efficient algorithm that require lesser computational resources, making powerful mathematical tools for signal analysis. In this line of thought, the DWT implement algorithm that allow successive filter and undersampling by factor 2. Each state, the MRI, is applied to DWT used to analyze the signal. In the figure 6, represent the iteration of low-pass filter or high-pass filter, where for the high-pass filter, output, we obtain, better say, the coefficient of the detail of level 1. And each low-pass filter, the processing is repeating to obtain a new coefficients. The example, we obtain two more coefficients like this. Is it freezing?
Technical problems.
Like this and this. A similar wave, how the filter works in the figure 7, that each iteration filter banding is reducing by half and the original signal. The original signal is this one, but when apply one level of the iteration in MRI process for the wavelet transform, we reduce the bandwidth to the half. And we repeat the iteration for the approximation coefficients. We repeat and reduce the bandwidth in 2 over and over again. If we can go deep in the level of the resolution. There's no change. A key aspect to this paper is optimize the process of the wavelet transfer for minimize the noising in this process. Sorry, I lose some equation in that slide. In summary, the optimization algorithm is based on the work of author Duff in J. Kosher, who implement an optimization algorithm based on the minimizing or maximizing cost, which why it's necessary to complete a data matrix with a condition. The condition, as we explain more slides further, that I propose the threshold optimization for this processing, then be able to operate this algorithm with this process. This slide I showed you in general way before the detail, the aspect that I into play for each the elements. First, the figure 10 show To complete the scheme that at the optimization step, the noise and the reduction process basis in WT and MRI. A typical process of the reducing noises is starting here and finish here. In this paper, we add another step here, taking the coefficients, the output of the optimization of the coefficients that eliminate or minimize the noising of the signal, and basis in the method of optimization, we try to get a new vector for applying the inverse Webel transform to recovering a new signal more similar the original than with less noise and better parameters without applying this optimization process. This is a little example what signal I use, a signal recording like a voice for 5 seconds, and a signal noisy. The development of this paper is based to applying optimization final signal reconstruction layer affected by additive noise. This signal enter in this part affected by additive noise and enter the MRI process, which is stopped by Gaussian noise. And following the MRI process, with signal reconstruction, finally applied the optimization basis on the data obtained for the above. Is the purpose to implement the simulation and the optimization platform shown in the scheme, considering to use different wavelet model that wishes at defined levels of resolution. All this with the purpose is being to able to effectively process the information and obtain also analyze data of the reconstruction process with the optimization. Finally, apply the inverse wavelet transform to obtain optimize the original signal that considering of minimizing noise to verify the performance and the process. We're using the norm, the mineral squares, and the signal to noise ratio. Important aspect that we can see, the threshold for apply the process of optimization is based on the data, the noise applying to the signal. Like this, we have the using this is the variance of the noise.
You are out of time.
More rapidly? Okay. It doesn't show you like go to results or
we can give 2 more minutes.
Huh? Yeah, okay. When finished all this processing in the figure 15, show the mean error square is lower than the better performance obtained in the blue signal. The blue signal is the signal that obtained the final process, adding the optimization process to the final and the MR for the eliminate noise. And in the similar way, and the preview, the norm is lower than the value indicate an optimization signal is much closer than the original signal. As followed in the graph, the high value choose grade the distance to the factor of the signal over the noise. This graph is the relation to the noise to the signal. When we have a high relation, we have a better signal. If we can see the signal output of the whole process, obtain better parameters that we no applying the optimization process to the MRI for the minimize the noise. And this is the data, the numbers we obtain. Finally, the graph, finally, the norm is the 11% better than we don't apply the optimization process, and mean error square is 22%, and the noise is 0.068% better. For conclusion, with the application of purpose processing, which improve applying optimization method of the later stage signal reconstruction using multi-resolution analysis implies 22% relative performance improve compared to not using it. This is because the optimization process through cost allowed optimization algorithm search the best and minimum value is raw to optimization matrix. The optimization matrix we are construct don't show you that, but this is a matrix we obtain with all this data we get before to get we obtain the final process of the inverse of Webber transform. Thank you very much. I'm sorry if don't show any figure we have to prepare.
Thank you, Luis, for your presentation. That would be all for session 3, and now we move.
Yes, now we will move to the second guest speaker today. I invite to, please, Jaime Anguita from Universidad de los Andes. We are doing some technical adjustment and we will continue. It's a eternal problem between Microsoft Word and Apple Word.
Good to see you. How are you? Oh, it's lovely to be back. Oh, no, yeah. Come on, Jay. Yes. How's life? Yes, yes. Fixing the experimental work. And yes. Other things about it. Applied, same as before. Working and working. So happy. I'm sure. We will. So, yeah, look forward to it. Yeah.
Está cargando. Activa la cámara, permiso.
La quitamos.
Sí, y el micrófono.
Yeah, it worked. But I lost everybody.
Yes.
Yes. But the organization is going to give extra gifts at the end because of this.
Extra coffee. Let's start.
Bueno, quiero dar las gracias a los organizadores. I'd like to thank the organizing committee for inviting me here. It is a real pleasure to be, presenting today in front of you. So, for me, this is an opportunity for, joining good friends, past friends, new people, exchanging ideas. So I would say what I'm going to present is just an excuse for just being here with you, okay? So, can I move this? No. Can I minimize this? Can I minimize this? Somewhere. Yeah. Anyway, this good friend here helps me with some details. Yeah, today I wanted to just I was offered to give a talk on free space optical communications, something that you are, I'm sure, well familiar with. And I'd like to also discuss about the challenges with you that we continue to have in free space optical communications and some of the research that I've been doing with my colleagues and my group at the Universidad de Los Andes. Yeah. We know that there has been an incredible expansion of data communication thanks to the development of optical communications, moving from RF to the optical domain has increased the data rate significantly at the volume that we can have today, thanks to the mostly because of the ocean cables that we have covering all the globe, allows us to have almost instant communications with many parts of the world in all kinds of services. But it hasn't been the same yet for free space optical communications because RF continues to dominate that part. And even though we have moved from carriers in the order of gigahertz to hundreds of terahertz, which means an increase in thousands for the potential capacity for communications. Nevertheless, we still face some challenges that are preventing us from expanding this, and I just wanted to discuss and share a few of those today. you change now to ice cream? Yes. Yeah. At the end, I'll acknowledge my the people working with me. So I'm going to go straight to what we are interested in. Okay. So you see that we still have an increasing volume of data per user per time, and we are expecting that Internet of Things will increase the demand of, and traffic. And many technologies, and we probably care more about this, affect more our human lives, and they require very little latency, like safety, healthcare, education, defense, and also a more humane interaction when we are distant from each other. And of course, communication for space exploration. So I gave a few examples of all the combinations possible you can think of for free space optical communications. I'm going to move forward with that. Just to mention that there are a few, out of this world examples of free space optical communications that are currently occurring. And one of the most amazing ones probably would be the laser communication relay demonstration that is going to very soon connect the space station to the ground, to a Hawaii station, using a relay, LCRD satellite, and the part that is missing that is going to be installed pretty soon is the Illuma-T, this device here that is covered, that is going to be mounted on the space station. Okay, but now, because of the time, we are more concerned about terrestrial free space optical communications. This is a nice view of Santiago that you may not have not seen before because it was taken in a pristine air. It's not always like this, but it improves, believe me, gets better, and it's getting better, I would say, every year. This is how it's going to look again in a few years when we solve all the contamination problem. But when we see this, we see an incredibly large opportunity for extending our data communication approaches and laser communications, along with, in general, wireless optical communication systems, will need a lot of physicists, engineers, and people working on this area. So there are going to be jobs for us. Okay, this is important. So free space optical communications, you know, is a point-to-point line of sight method that uses light for carrying the information data. This is a very simple example of a system like that. The most basic way of conveying the information would be changing a property of the light. And the easiest one is to change intensity. Yeah, the change of intensity would carry the digital information that we are trying to transmit from one point to another. And if we want to have full capacity of free space optical communications, we need to use not only incoherent intensity-based modulation formats, we need to move into coherent systems, because that's what is going to give us, you know, the full potential of links like this, among other things that I will discuss briefly. Now, some of the challenges we keep having with FSO: beam acquisition and pointing and tracking, which is a mechanical problem; optical attenuation because of propagation, and also because of the components we are using for this; cloud cover and fog. I will mention something at the end, which is part of the atmosphere; angle of arrival fluctuations, beam fragmentation, loss of optical coherence. This is important for coherent communication. And the fact that we need to devise new signal modulation schemes and carrier multiplexing. And so atmospheric absorption is something that we always need to think of for beginning to think of a system like this. And the choice of wavelength affects both link's performance and detector sensitivity. So I've shown you here what you get out of the simulation system. I forgot the name. Is this software that allows you to have the transparency of the sky, Modtron. And I did this calculation for the typical situation in a summer time on Mediterranean latitudes, and you can see that wavelength that we can usually use in our labs are possible windows for communications in the atmosphere, particularly 1550 nanometer, which is the wavelength that is used in fiber communications. So for that, we could have ideally a transparent connection between the two if we solve the other problems. But we also can use visible light for transmission across the atmosphere. The limitation would be, in that case, the eye safety because of regulations, even though we still don't have written regulations in Chile. There are international regulations for the amount of power we can use because of the focus on the visible light in the eye, okay? But there are different wavelengths and regions where we can test different approaches. Fog continues to be an extremely difficult problem to solve, and this is a simulation where it shows that when you have very low visibility, is doesn't make much difference whether you're using one wavelength or another. When the visibility is larger, you can find some differences, and 1550 nanometer seems to have a better transparency and in this regard. Okay, there are some efforts being worked in the lab, in some labs, on how to make a channel through the fog, but this is still something that is experimental, nothing developed yet. Okay, what about rain? Rain is more beneficial than fog, and if you've done experiments in this, you will see that the attenuation may be up to, say, 4 to 6 dBs per kilometer if you have moderate to strong rain, which is much better than what you would have in fog, which can reach up to 200 dBs per kilometer. So in an FSL system, you would expect, and I have a pointer here, if you start with a Gaussian beam on your transmitter side, on the collecting lens at the other end of the link, you would have everything distorted some part of the light obviously will be outside. The beam spot is larger than the receiver aperture, and it's going to be fragmented. On the detector side, so on the focal plane of the receiver, you would have a fragmented point spread function that is also dancing on it, and that is going to cause scintillation. So our channel is a randomly, some people say isotropic or maybe anisotropic if it is near the ground, anisotropic distribution channel. And so from the perspective of turbulence, I mentioned angle of arrival fluctuations, beam fragmentation, loss of spatial coherence. In these examples here, I show, what it looks like of the beam reaching the pupil of the receiver, and that will be the dancing of the beam of the focal plane. Certainly, if you have a small detector area, that is going to show significantly large fluctuations. And those fluctuations, these are experimental, by the way. So these are the kind of fluctuations you could get on your receiver because of a strong turbulence near the ground. And in this case, a scintillation index is 1. So you have deep fades here that are very difficult to counter, at least with just a simple system like that. So a good design needs to minimize the symbol error rate, and not only that, also increase the link availability. So it needs to be working all the time or most of the time, okay? And these are very dependent on the channel. So solution to improve this? Yeah, people have mentioned in the past, aperture averaging, spatial diversity. That could be multipath or best path, multi-mode. If you use specialty modes in laser beams, wavelength hop, that is only meaningful when you have a large wavelength separation, adaptive optics, pre and post compensation, modulation formats, and multi-hop links, something that Professor Sacvlc have done in his group, I remember. So one of the ideas is spatial diversity. So what if we have different beams on the transmitter side? So like a meso system. Could we reduce the effect of scintillation? Could we reduce the number of the magnitude of those fluctuations to improve the quality of the detection? Well, that will depend on whether we have uncorrelation between the signals, the paths that are transmitting to the detector side, okay? So we need to ensure that the diversity, and that will depend on propagation length, turbulence strength, and beam separation. And in this plot that I showed here, you see, when you have a short distance, 1 kilometer link, you need shorter separation to achieve uncorrelated between the two paths. But as you increase the propagation distance, for example, here 9 kilometer, then you need a larger separation between the transmit beams in order to have that uncorrelation that you needed in order to reduce. Reduction, nevertheless, is not something that could mitigate totally the problem. You still have temporal fluctuations that I may address later if we have the time. Okay, one thing that inspired me to work experimentally with diversity was, for example, this work published that began later, much earlier than this, but the group led by Anton Zeilinger in Vienna using beams with orbital angular momentum, in this case, a very slow transmission rate system, only just to demonstrate the principle. And the beams wouldn't be detected by any detector, but just a camera that would be later on translated into a symbol just to demonstrate that you can transmit images. But it was a proof of principle. It was well published everywhere. So, but the way that we've seen this is, what if instead of using multiplexing, we use OAM for creating a different diversity, symbol diversity? So modulation using OAM. So we could pack, a sequence of binary bits together and define a symbol. So in order to do this, we need to select a large number of OEM states that is going to be our full set. And we can activate a few of those OEM states to form the same symbol. That's the idea. These are examples that we did some years ago in the lab. So superpositions of two OEM states, a negative and the positive, and they form different shapes. And those black lines you see in between are the phase cancellations that are produced because these are coherent superposition of OEM states. So lately, we've been building a test facility at the Universidad de los Andes. So what I'm showing you here at the engineering building that was built not long ago, we have in an office for now, it's going to be moved later, we have a folded system, propagation system. We have transmitter and receiver on one side, a remote system on the other, and about 500 meters away. So I'm not going to go through details. We don't have much time for that. And we've been using visible light because in order to use telescopes, those that are off-the-shelf telescopes, they're coated with the coatings for visible light. If you want to use infrared light, you need to order your special coating, which is very, very expensive. So, but we'll be using something that is very practical, has been monolithic. We have designed a monolithic system that transmits a beacon for alignment, also for measuring the strength of the turbulence. And the big scope here is used for transmitting OEM states. So we expand the beams so that the diameter is sufficient so that we can have a compact diameter on the remote side and also on the side of the receiver. We currently produce OEM states and transmit OEM states up to topological charge 45, which is the amount about the maximum that you can get out of this tube here, 14 centimeters. Now, so the idea we're using polarization. So we print OEM using a spatial light modulator or SLMs. SLMs use a polarization alignment that is on the longer axis. So in this case, on horizontal axis. So in order to transmit both and have the ability to receive both signals, the beacon signal and the OEM signal on the same receive telescope, we are rotating polarization. So the OEM is transmitted with horizontal polarization and the beacon with vertical polarization. We rotate that. And so on the receiver side, you will see this is remote station, 500 meters away. This is the beginning of the night. You can see some of the light there. The two mirrors are mounted on a gimbal mount that is controlled remotely. The mirrors are not very large. These are 4-inch mirrors, so 10 centimeters each. So we need to focus the light, the beam on the mirror. The focal point, of course, at that propagation distance is very large, so that we can have a matching diameter on the receiver side. That's a short video that I show the amount of turbulence we can see. This is seen from the transmit side. So maybe from afar you don't see all the turbulence, but it's very strong. Now, on the receiver side, we've mounted a 2-branch receiver, also monolithic, that is here, so that we could have the OEM that is entering this Schmidt-Cassegrain telescope, and inside it is split. The signal that is measured for turbulence strength determination and also for recording data, different kinds and high-speed cameras, and the OEM. Now, since we are interested in communications and using modulation, we are trying to find a good systematic way of detecting the topological charge of the OEM beams. And now we're using a shock Harman sensor, okay? In order to do this, we need to compress. Imagine this, we have a large beam. We cannot analyze a large beam. We need to do a compression. In this case, we're using 55-time compression so that at the output of the oscilloscope, after the eyepiece, we get about a diameter of the order of 3 to 5 millimeters. We are currently not using any adaptive optics.
point, even though we are working on that idea. So just a quick example of what you could see. I'm holding a piece of paper here in front of the receive telescope so that you can see both the OEM, very distorted, and the beacon that is also very fragmented, that both entering the receive telescope. And these are typical OEMs, single state OEMs, one that is nicely, disturbed, and the other one harshly disturbed by the turbulence. That's the kind of thing we're receiving, and even though the strength of the turbulence, as I'll show you in a second, we can still decode the content of the topological charge and distinguish them. So briefly, I'll describe one of the things we've done for detecting or measuring the strength of the turbulence. We're currently using two systems. We're using a position sensing device that allows us to record the points, the point dancing on the surface of this. So you can see here, this is the image dance produced by the centroid of the beacon, dancing all around, and the diameters are varying depending on the strength of the turbulence. So the larger the turbulence, the more the dancing. This is related directly to the angle of arrival fluctuations, okay? So these are the intensity fluctuations seen by those, by another point detector, and these are the centroids dancing on the X and Y axis. What we always have is temporal correlation, of course. This is an important aspect of this. In this case, it was because we have a kind of a stronger wind. We have a correlation time of 6 milliseconds. It could vary from 2 to up to, when it's very slow and quiet, 20 milliseconds, the correlation time or the characteristic time, okay? So from that, we get an estimation of CN squared, which is one of the ways to represent the strength of the turbulence. Well, this is not all, because when you're transmitting, you need to know the propagation distance. So you can transform this or use this to put it in terms of the Fried parameter, for example, or R over D. So these are the measured CN squared values that we have obtained in one of the campaigns. The values are really, really strong. We are about 15 meters above the ground, passing through two roofs of large buildings that are accumulating heat during the day. So we usually use this in the evening. So the strength of the turbulence varies in this case. So in the order of, say, a fraction of 5 or 4 times 10⁻13 up to, say, 4 times 10⁻12 is very large. These are two examples. These were performed before. This is a shorter distance, but so that you can see what happens when you transmit a coherent superposition of two OEM states, these -20 and 20, -30 and 30. Of course, these are recorded with a fast, high-speed camera, 1,000 frames per second. So the speed here is reduced like 30 times. Okay, in reality, this is much faster. This is nice. This is what we would like to expect. This is not the reality most of the time. But the idea is we want to have a detection with a shock Kalman sensor. Why this? Is a possibility. We've worked with also with the other device, the mode sorter, developed by an approximation of that, developed by the Glasgow group. And we realized that this is very, very practical. We already had a shock Kalman for adaptive optics. And so we're reducing the number of subapertures. I don't have time here to describe the purpose. You can find this on some of our publications. But the idea is that vortex beams, because of the wavefront that it has, it projects spots that are away from the central of the subapertures. For a plane wave, you have all the spots on the central parts of the subapertures. If you have this wavefront that is rotated, that is inclined, then those spots are going to shift. And that shifting is proportional to the topological charge. Now we devised a method that is we call local OAM. say something in a moment. But look at this. These are the kind of recordings we're getting. The area here is 5 millimeters, okay? So OM state 15, 25, 40. Look at the even though this is not an intensity, this is not a camera image, just the spot from the shock Harman sensor. But you can see that they distorted, they are off center, they are unbalanced in terms of intensity, and we can still derive the values. We're using in practice 17 by 17 of apertures, each with 60 by 60 pixels. Calibrating this takes some time. Once you learn how to do this, it works very nicely. But it took us some months to do it at the beginning. Okay, this is an example of an intensity field that we're looking at. Okay, this is the kind of distortion we're getting. This is with the high-speed camera. Now, I'm going to finish with this maybe. Not time for quantum part. But if we produce this local OAM map that is multiplied by the intensity image coming from the shock Harman, you can find it on our publication. We can produce a histogram, OAM histogram of values. Even for a system without any turbulence, it's going to produce an extended histogram, okay? Because each and every point, we're not calculating the centroid, because the point could be totally fragmented. It wouldn't work when you have strong turbulence. So we calculate the OAM contribution for each and every pixel that is illuminated. We multiply this local OAM map that is calculated once only for the system, and we get this histogram. One easy way, when you have a single OAM state in the light, you simply calculate this. It's a simple weighted average, and you get the OAM state you're looking for. Is it accurate? It is. I'm now redoing everything in the lab without turbulence to show that this is very, very accurate. So the amount of deviation is less than 0.1. So this is an example. OAM state 30 transmitted over a very strong path, 6 times 10 to the minus 13. And the estimated value after that, applying that formula was 30.5. We do this with many images. In this case, 400 different images, okay? Uncorrelated images on the same time of the day, of course. And this is the histogram we get. So this is the quality of detection we're getting by doing this with this method. And this is an example of this situation. It's actually in the same recording. We don't need to have a center OAM beam on the plane in order to get the accurate. So more examples. I won't stop here because it doesn't matter. Just the idea that the quality of the detection varies. We don't understand exactly everything that is going on. We're still learning about this, but nevertheless, we are trying to find the narrowest standard deviation of all the detection we get from the images, 400 images each. Because the better this is, the higher density of OAM state we can have within a range, right? I'm gonna skip this, maybe this one here, and that shows how much the turbulence is varying in terms of the incursion of the beacon spot in the plane. So this would be strength of turbulence in a way, and this would be OAM spread. And it varies depending on the kind of OAM that we're testing. So I'm not making any claim yet, but it seems that it matters the sizes of the scales of the turbulence in terms with respect to the sizes of the diameters of the OAM state we're trying. And this is just when we compare scintillation index, which is kind of a more standard comparison. So This, we have two OEM state together, coherently superimposed. This is the histogram of one of the images. And these are the histogram of 400 or 200, I forgot this, of all the images, showing clearly that we can detect the two superimposed OEM states, regardless of the strength of the turbulence. Yeah, I don't think we ran out of time, right? Okay. Just one thing that this is just, I put it just because I like the picture. Maybe some of you have seen it. Yeah. This is the free space link, quantum space link between the Tenerife and La Palma, Canary Island, by the group led by Anton Zeilinger. They've been working on this with other people that I haven't met yet. So they have a nice experiment to show that, because the idea of quantum transmission of quantum states will be something interesting. Some people claim that, oh, we don't need this yet. With the increasing capacity of the quantum computers and eventually their connection to our networks, this could be relevant if we want to have secure communications. And so I find this a very nice approach and show how we can use entangled states. So entangled states, for those who don't know, is having two photons that are generated with the same source on a nonlinear crystal that have properties that are inseparable. So if you modify one of them with one quantum information, the other one, regardless of its location, is going to be modified accordingly. So I'll skip this, but I'll show you that. So we are also working in spatial diversity for quantum transmission, and we are being helped by the Quantum Future Group in Università di Padua. We have designed a system that the idea of using diversity, which is something common and known in classical FSO systems, we try to do it with quantum, which is a different story, because when you are transmitting a single photon, then you don't use the two paths, you use one of them. So what we're trying to do here is select the best path every time by checking with a beacon how's behaving. So this is one transmitter. So we have the beacon here with a dichroic mirror. This is the quantum signal on green using an off-axis mirror, so that the beacon here at the end, they're collimated. It's kind of tricky to do in the lab, but we have done it. And now if we have two of those transmitters and we have one receiver, we could do this detection, and with the system on the receiver side, we can check every other millisecond how's the quality of the channel and send a feedback signal to the transmitter. Since we're doing this with pulses, we need to know which of the channel it is, because we have one receiver on this side. So we use just a simple delay with optical fiber so that we can have one pulse that is, in the order of 2 nanoseconds, and the following one 10 nanoseconds later. And that's the way we can distinguish the two of them to know which channel it is. So it's been tricky. We're doing this in the lab only, not yet outside, but that's the plan. This is a build system. So the idea is that we can separate the two transmitters apart to find the the position where they are actually uncorrelated. And this is the receiver side. And one important thing, can we trust the beacon to see if this is going to be working for the quantum domain? Yeah, we found that in the lab that the correlation is 0.8, so close enough so that we can use this. But we will see what happens outside. And it's going to require the help of our friends in Italy. And that's the gang, the group. Most of them have graduated here. These are the PhD students and postdoc that recently joined, that is going to work in adaptive optics. And our PhD program and master's program is always open for interested and motivated students who would like to work in theory and, of course, in experimental demonstrations. So thank you so much.
In order to keep our program, I offer 2 questions. Someone want to ask? Another question? The last one?
Classical density modulation direct detection is quite depending on the device's bandwidth. So the quantum is the similar case.
Yeah, so people still starting to work with the section that is fast enough. So speed is not something that is at this point. The first application is the low hanging fruit. Speeding. That is we have a very long dead time that prevents them from having something fast. At this point, I would say most of the part seems to be working on, operating with those highly sensitive detectors so that you can reach very low levels of detection, including in daylight, which is also a number of other that evolve the rest of the light. And but because of that lag time of those detectors, I would say we're still far from having high speed.
Excellent, Professor. So I started working on FSO about 10 years back with Fari as PhD student, and we have done a lot of experimentation on turbulence and fog. We saw the similar situation for intensity modulation, direct detection, yeah. But you have done a great work in turbulence. Do you have done some work on in foggy attenuated channels as well? Okay. So what's your comments on that? I mean, that is the challenge that we can.
Guiding channel, half a meter long, with the intensity, with the information signal low in the channel by the dissipated fog from this high power. Grading exactly. It is. Yeah.
Please keep some minutes. I will invite Fari. Yeah, because the organization wants to recognize the valuable work and research of Isaman. Isaman? Iceman? You? Osman, sorry.
I think it's a presentation about our keynote speaker. Unfortunately, the stand couldn't be here, but we will take it there. The organizing committee has got some people to say thank you. I mean, these guys have put a lot of effort and shared time with us, the tone of appreciation. Some people, you know,
No.
Yeah.
No, it's so, and of course, to hire.
Yes, I mean, no, you're the CD. Yes, this is you have to hear please euro. Yes, but it is, I don't know what it is, but I'm yeah. I just want to say thank you very much. Yes, for being here and for sharing this and thank you so much. And then this is for Osman. Osman, this is your first gift from our organizing committee, and we wish you the very best. You are the youngest. Normally, I think this conference really we have two couples. I'm going to be just before the table. So we have to keep that back there. So thank you so much. And the coffee, yes, there is a coffee. This is the only conference I've seen that they keep you here for hours. They give you coffee after
15 minutes coffee.
30 minutes or 20 minutes? 15 minutes. 1-5. Please come back here because we are running it today. So please, if you want to eat your coffee here or your food, whatever it is, 15 minutes.
6G is saying that it is predicted 6G will meet all of those. I honestly myself not convinced. But that there are interesting things that we can look at in here, in energy efficiency, spectrum efficiency. These are directly relevant to us. We can pick up those, see that what is the target, and therefore could we aim towards that? And then is it possible to meet or not? Time will tell, I don't know. Okay, and of course we had this presentation this morning about this. These are various applications. I don't want to go through this. I just want to go fast through this. Okay, this is interesting. We have IoT needs technology is what businesses and so on, but things are happening. AI, machine learning. This is a buzzword now. We stop with what does actually mean AI and machine learning in wireless communication? Does it apply everywhere? And we do a lot of simulation about these things and so on. Does it actually really matter that if I gain 0.01% efficiency, but I'm putting 20% more resources into that? You know, these are questions that we ask. And then for us, unfortunately, this is the killer. Wi-Fi 6, Wi-Fi 7. They're going to deliver up to 10 gig of data. So VLC is finished. What are we going to do with it? Is it the end of the road for us? Or actually, there are new opportunities for us. So watch out that space. This is really important, yes. And a few more slides, then I will finish that. Innovation is interesting part that we need to consider. You know, there are many, you can read this yourself, that we will need to address when we are writing research proposals. What is the innovation in your world? Significant impact, KPIs, and so on, game changing. These are the buzzwords, yes? And we need to, in any research, we need to identify a few of them and latch on into that, yes? That is important. You guys do it, or we all do it. These are more, you know, that we can have, okay? Now, RF technology. Our RF colleagues is still convinced that optical wireless communication is a dead horse. They honest, genuinely still believe it. We as a community for the last 30 years have been trying hard in order to convince them that that is not the case, but they still part of it believe it. But we need to highlight issues that they, you know, we can latch on to. You know, bandwidth bottleneck. That still is the major issue in RF. No matter what you push the frequency, you're going to have that. So they cannot get away from this, okay? And this, of course, you know, if you push the higher frequency and so on, then you have going to have this. How are we going to address those problems? Okay? They may say that we will do that, but try to do all those things together. It is really difficult. Okay. And of course, Osman showed this slide, but this is a very important slide. This is very, very important that we look at the impact of technology, especially wireless technology. It's a very high frequency to human, planet, other species. And this is becoming a concern of many countries. We see it in UK that base stations are not allowed in certain areas. People burn them down. They bring them down the base station. In areas where there are a lot of children, the housing areas, they don't allow them. So they had to hide these space stations. They disguised them. But people find out and destroy them. If you move to higher and higher frequency, narrow beam, highly concentrated, if you're going to go massive MIMO on the street level, my God, what is the implication as to us walking around the street bombarded with these high frequency signals? This is an issue that we need to be aware of that. Okay? And I don't know, United Nations is aware of that. They put limits and so on and so on. Okay? Then I've got a few more slides and then I'm done. Okay? This is an interesting, is now developing as a way forward. Before communication engineering, we were isolated. We were strong. We could do everything possibly on our own. That is finished. This is the future. If you look at the European Horizon goal, there are a lot of integrated systems, integrated technologies. And integrated technologies are these, combination of these things. You can see that last one, integrated sensing, positioning, data communication. So therefore, what Europe is looking for that, we don't want too many devices. We want single devices to do all three, which is logical. And then on top of that, you can add sustainability and renewable energy and closes the circle. Okay? And I just go to very quickly to just to show you that. Can you just go to the last few slides? It's faster in your system than me. Okay. You see, I just wanted to show you this. Sorry. Leave it with me. I can do that. Okay. Done. Okay. Go to the last few slides, and then I am done. Yeah, that's fine. Let's stop there. So, okay. I wanted to show that what industry does. That's what I wanted to show you. Is it? Okay, let me just. Okay, anyway, so it's anyway, there was a slide that I wanted to show you that the global community in VLC communication is actually huge. So the common denominator is the VLC solution. But in my personal view, VLC for indoor environment is the future. VLC's future is underground, tunnels. These lighting systems will never ever be used as a solution. We will have one. So think of beyond this into places where RF cannot operate. And also think of infrared. In places like this. Underground VLC, because you need light. Here, I can open the window. There cannot get my natural light. Why do I need to turn this on? Because it's finished. What am I going to do about it? I can have infrared if I want. Anyway, I just wanted to share this with you. There are a few things, yes. We know where we stand and so on. And hopefully that out of this will come new ways of thinking. I'm sorry that.
We follow with the session number 4. Now this session will be shared by Diego Fuentealba.
Thank you. Hello, my name is Diego Fuentealba, and I will share this session. Okay. So for the presenter, please keep like maximum 15 minutes for the presentation, and I will notify you, I will advise you at 10 minutes. So to keep some time for questions. So that is the main idea. Okay. Okay, close. Thank you. I can see a change in the program. So it's here Otman for experimental demonstration of an optical camera. Oh. Okay. No, but somebody, I, but okay. So maybe we can keep the program. So in this case, is Jesus the first one, but Vicente asked me to change the presentation because of Otman wanted to. Otman is having a meeting, or something like that. So. No, but in that case, maybe Jesus. Yes, you are with the first one. According to the program. Yeah. Okay, Jesus will present a comparative analysis of 5G digital twin microservice with FSO integration.
No? Yes? Okay. Yes. Hello everyone, my name is Jesus Saez, and I'm going to present my paper, which title is Comparative Analysis of 5G Data Twin Microservices with FSO Integration for Underground Mining Ventilation. So here we have the table of contents. We have a brief introduction, the methodology, system description, study results, and conclusion and future works. So for the introduction, with the development of sensor technologies and their relevance to the mining industry because of the measurements of environmental and operational parameters we can obtain from them, and due to the huge amount of data the sensors collect, one of the main challenges of the process it's how we can process the data in an optimal way to improve mining safety and operational efficiency. Which is why it is necessary to focus on an architecture based on microservices, allowing scalability and compatibility at the same time. And what is microservices? Well, microservices is an orientation, a software orientation architecture focused on creating applications composed of smaller, independent services that communicate with each other and enable larger tasks to be carried out. This improves the scalability of the applications. Here we have the experimental setup. On the setup, we have the model of mining galleries. Marked on red, we have all the sensors configuration. We have sensors that collect data from gas sensors that collect CO and CO2, a temperature sensor, differential pressure sensors to measure the flow of the air inside the galleries, and also humidity. In green, we have the SOC, the system on a chip, specifically Jetson Nano, which have a 5G hat connected to enable 5G communication. This make the downlink and also the uplink. And in blue, we have the actuators and motor and a frequency variator to make possible the airflow through the galleries. So the methodology. We have one main problem here, which is how how to answer the high demand of data at the same time we try to answer the real-time demand. The proposed solution is to integrate new technologies such as 5G that also have many benefits with FSO technologies to propose the coverage through the mining gallery. We have the system description. Here we have the system diagram of a digital twin. We can see the inputs that we have from the Raspberry Jetson Nano. We have all the TIC stack that is a collection of different technologies based on time series. And we have also some engines focused on MQTT protocol. So what is digital twin? Digital twin is we have the real world entity, we have sensors, and we collect the data from the sensors. We save them on a database, and with that, the flow of the data, we create a virtual representation. So we can have the responses of the real entity through with a virtual representation of it. So what is the TIC stack? Well, the TIC stack is a collection of technologies. As I said before, we have chronograph, we correspond with the user interface of the whole TIC stack, and it is used to configure the charts and data dashboards in InfluxDB and integrate capacitors alerts. Also, we have InfluxDB that corresponds to the time series database series system, optimized to provide time series data and its storage in association with time and value. Telegraph provides a metrics collection and metrics collection agent that is used to collect and send them to InfluxDB. And finally, we have Capacitor, that it's a metrics event processing and alerting system application used to decompose time series into actionable alerts and send them to the system. So there we have MQTT protocol, and what is MQTT? It's a machine-to-machine protocol that communicates. Its communication is based on publisher and subscriber. So in this approach of IoT devices, the sensor, the device connected to the sensors have the task to publish in a specific topic the data that collect, and then through a MQTT broker, and then the subscriber have listen the data that is submitted and make some actions if a certain threshold is trespassed. Here we have the study results. Well, in the study results, we can see the different measurements of latencies that are a result of the data we sent. We use a DHT22 sensor to send temperature and humidity data through the MQTT protocol. And this is the latencies we have measured. We have Wi-Fi, 5G NSA, and FSO. As we can see, the greater latencies are from Wi-Fi technology, and the lower are from FSO and 5G NSA. Also, we can see the average values of every one of them. And here we have a distribution graph that we use to see how stable, how close to one value are the latencies measured. So as we can see, here we have the Wi-Fi in blue, and the values or the latency distribution is between a range of values. And for example, with FSO, we have all the values concentrated or closer to only 1 point, and that we can conclude that it have more stability of the system. That said, we have 5G NSA with its characteristics on the graph are very similar to FSO, so also are more stable. Why that is important? Because we are in a world that it's evolving into streaming demand, and it's very important in streaming demand to have stability of the system, because it's important to not lose any bit. So as conclusion and future work, it is plausible to propose this communication system as a candidate, integrating predictable analysis in the downlink and processing with 5G technologies, resulting in a notable improvement of 78%, reducing average latencies from 81 milliseconds to 18 milliseconds, compared to traditional Wi-Fi technologies. So the obtained latencies are close to the real-time range, which enables ventilation on demand applications through microservices implementation. And MQTT allows greater scalability. So it's interesting to see how possible it's to integrate this protocol to other technologies. Maybe, for example, including encryptation, like quantum encryptation. And that's all the presentation. Thank you for your attention.
Thank you for your presentation, Jesus. Any question? Question, please. Okay.
Okay, thanks for the presentation. I just have a quick question. I didn't understand quite well if the results presented are simulations or they are based on the experimental test bed that you have in the lab.
These are based on the test that we made using the model, the experimental setup, and the protocol that I presented.
And as future work, are you consider actually going to an underground mine to verify everything?
Yes, that it's one of the main goals, to prove this system in a real environment, a real mining gallery, for example.
Well, I'll talk to Ismail because we have access to a mine right now.
Well, we can talk. I can pass you my contact. Perfect. Yeah.
Thank you. Any question? No? Okay. Thank you. Thank you, Jesus.
Thank you all.
Okay. Let's move on for the next presentation. Okay. Carlos. Characterization of a perovskite photovoltaic base optical receiver. Thank you, Carlos.
Thank you. Hello, everybody. I'm Carlos del Valle. I'm a PhD student from Carlos III University of Madrid. And this work is a joint work with Northumbria University with Professor Fari Osman and John Q. Tao. And in the University Carlos III, Juan Carlos Torres and Jose Manuel Sanchez. And Iñaki Martinez from the company Optiva Media. This work is entitled Characterization of a Perovskite Photovoltaic Base Optical Receiver. This is the roadmap of this presentation. We are going to start with a brief introduction about the optical wireless systems and we are going to talk about our problem statement, and then we are share the results that we have obtained and the conclusions of the figures, and we are going to share a possible use case. As you know, optical wireless communication system, as whatever system of communication, has two entities, a transmitter and a receiver. The transmitter consists of basically in a modulator that set up the signal that we want to transmit using an LED or a laser. We have the channel, and at the receiver side, we can have a pin photodetector or APD photodetector, and then demodulate in order to decode the signal. These are 8 possible use cases of optical wireless communication. The first one that we can use, we can fill up our gas tank while we are connecting to internet, and in the case of vehicle-to-vehicle communications as well, and for underwater communications, visible light positioning, cyber secure solutions. We can use optical wireless communications as a QR code as well. And finally, in places like national heritage, where it is impossible to drill a hole in a building, we can deploy optical wireless communications. What is our problem statement? The problem that we have detected is the saturation of the PIN photodetectors or APD photodetectors when they are exposed over sunlight. In order to, and we have noticed as well that the previous use cases of optical wireless communications are really implemented only for indoor environment. That because of the problem of the saturation of the photodetectors. In this way, we are going to propose the use of photovoltaic cells based on perovskite in order to try to carry out this problem. As well, the photovoltaic cells based on perovskite can be cheaper to manufacture instead of silicon solar cells. And as well, the efficiency is better. It could be better than the silicon photovoltaics. We can see here a comparison between when we have sunlight with a solar cell. This is the BER and APD photodetector. We can see that the BER is much better in the case of the silicon cell. And about the APD, this is our response, and this is the response of the silicon solar cell. We have noticed a difference around 15 dBs. And after knowing this, we are going to try to replace the conventional photodetectors to a flexible perovskite in order to study its viability to develop a self-powered receiver. And in this work, we are going to characterize 2 different sizes using the same substrate. The first one is 4 millimeter square, the active area, and the second one is 0.49 millimeter square. The measurement about the responsivity and the equivalent quantum efficiency, we have noticed that we have the peak in the blue color and other one in the red color. However, we can use it in the near infrared spectrum as well. About the PV efficiency, okay, we have, if we increase the voltage, we are going to decrease the photo-generated current. And this is the maximum power at the maximum power point, because after this point, the cost of increasing the voltage is to put external current to increase the voltage, and we don't want that. And the figures of the efficiency are around 4 and 5%. With regard to the bandwidth that we measured was in open circuit conditions, because we want to generate current with the solar cell. We know that if we connect the solar cell in reverse bias, we are going to achieve more bandwidth. However, we want to self-power the receiver as well. And for the smallest size, we achieve 70 kilohertz. And for the biggest, 4 millimeter square, the bandwidth was around 23 kilohertz. With regard to the bandwidth, we know that the bandwidth can be limited by the transmitter or by the receiver. In this case, we have used a micro LED that has 67 meg. It means that in our case, the receiver side is which determines the bandwidth. In other words, it means that this value depends on the capacitance of the photodetector, and it is related to the active area of the photodetector. That, in other words, the higher area, the lower bandwidth. Before the conclusions, we are going to share with you a possible use case that we have developed with this perovskite. We developed a visible light positioning system for underground environments. And we have developed the receiver that consumes around 10 milliamps. And as well, we have developed a gateway, a Bluetooth gateway, in order to see our position in the mobile or tablet. And this is an effective prototype, effective cost prototype. The receiver costs around 10 euros, and the transmitter, based on Arduino Nano, it costs around 12 euros. We can give you a discount for today's presentation. About the conclusions, we have two maximum values for blue light and red light, and as well we can use infrared. With regard to the figures of efficiency, we have 5% around. And we have noticed that to have 3 volts in order to power supply a microcontroller and amplifiers, we can connect in series some small modules in order to obtain 3 volts. And to increase the current, we can increase the size of the photodetectors on the rails in order to achieve that current. With regard to the bandwidth, we are interested to work in smaller areas in order to obtain more bandwidth. And as we mentioned before, we can develop wearables like a bracelet, helmets, and so on. And that's all for my side.
Thank you for your presentation, Carlos. Interesting scout. So, any question?
Thank you, Carlos, for your very, very interesting presentation and inspired that you saw for us. I have a question about the perovskite DV cells because you share with us your setup in your positioning system. You can put the image, please.
Yeah.
Yeah. There. So what the purpose that I found in the lab for myself that it's very, very difficult to compensate the orientation of the PD. So my question is, are you discover what is the behavior of this kind of PDs when you change the orientation of your photodetector?
Very, very.
It's different from the pin, for example?
In this use case, we can move very quickly without affect the reception. Even here, you can obtain signal.
Okay, and if you rotate, for example,
perfect.
It's different from the pin, from the pins, because the pins are very sensitive.
Yeah, no, completely different. Yes.
Okay.
And you can have light from the windows and without having any degradation.
Another question. Can you tell us more about this non-sensitive to solar light? Because it's a hard one. Instead of pin sensor, when you expose to the solar light, everything is blowing up. Okay, but instead, what is the advantage of that? Because I didn't get it a lot. So if you can explain more.
Yeah, for sure. In the practice, for example, we develop a prototype to receive 4K video, okay, for a car, and because this is the topic of my thesis. And for the first set of tests, when we put the system, we had a lot of degradation because of the sun, and I couldn't receive the enough level of power of the signal for that. And for that demo, I had to cover the window of the car. And after that issue, we started thinking about how to improve that. And the idea of the photovoltaic cells can be interesting for us in order to to power supply the receiver as well, to face both cases.
It could be interesting if you mix the solar cell with that photodiode and you can select just the solar part. For example, if you capture, because solar cells capture just the sun, not other lights, okay, associated to solars. So if you capture this and you mix with your signal that it's mixed before with the solar, you can cancel this component with that part of the solar cell. So you can just make the suppression. It's like a cancellation in sound, I think.
Okay.
It could be an interesting idea.
Okay. Thank you for the idea.
Thank you for your presentation.
You're welcome.
Okay, we have the last question here.
Hi, Carlos.
Hi, Juan.
Thank you very much. Did you say that you are using GPS?
Could you repeat the? I can't
Are
hear
you
you.
using GPS? GPS?
No. With this one,
Yes.
we send the IDs with the position, and then we can send the position to the laptop, but we are not connected to the GPS by RF. Is it the question or?
No, because I appreciate your offer, you see, to offer your product, but the problem that you have, GPS doesn't work in an underground mine.
Yeah, for
there
sure.
are no signal that
Yeah,
from
for sure.
satellite. Yes.
This can be a possible solution for underground places.
Could be, yes, but you have to take the universal time signal from outside.
Yes,
in order to synchronize GPS.
Yes, yes, for sure. We would need to synchronize all the emitters in order to know it. Yes.
Yes, because you cannot trilaterate inside the tunnel.
I can hear you.
You cannot trilaterate. You can do trilateration.
You can do
trilateration inside the tunnel.
Okay.
Yes.
Trilateration.
Yes, it's a positioning.
Yes. We have another prototype based on a semi-sphere with perovskites with that idea, with trilateration, in order to obtain the position, and the platform has it is around 50 centimeters.
Yes.
And the maximum error was 4 centimeters. And we started with a setup of measurements with 100 points, and only 1 point was failing. Only one.
Yes. Are you using inertial position system? In your prototype?
No.
Maybe perhaps you have to think about that.
Okay. Inertial.
Inertial.
Okay,
Yes.
thank you.
Okay, thank you, Carlos.
Okay, thank you.
Another applause.
Thank you.
Thank you. So move on for the next presentation. So Vicente, you will present experimental demonstration of an optical camera.
Me again. The controversial guy. So right now you can call me Othman.
Okay, you can start.
Okay, I apologize for the change of plans, but this was part of Othman's presentation before. This is paper we submitted to the conference, and I was supposed to be on this session, but he was counting on presenting it before because he couldn't be in this moment. So he asked me if I could cover him, and here I am. It's not me. So this is work called experimental demonstration of an optical camera communication system using large off-the-shelf LED panel. I have the, yes. So in IoT systems, we have been interested in using cameras as receivers, but we noticed that if we get far away from our sources, they become dim and they become small, so it means they are more difficult to find in the frame. So we thought, let's take advantage of these large transmitters that now are available in most roofs. We also have them here at the hallway. And let's see if we can use them to transmit large amounts of data. And in this way, we could, for example, do positioning. If we have large IDs, we know this lamp is this ID, and then the other lamp is another ID, and we can do trilateration and all these fancy algorithms we have heard. So we use the big transmitter for getting better signal to noise ratio. And we receive it with a image sensor, which is embedded in a normal camera, the same we have been talking about the whole conference. And I believe the biggest contribution of this work is on the current source design. This is going to be very helpful for people who are starting with VLC or OCC. So what we do, we simulate first, and we develop this circuit, which is a voltage-driven current source. It can go deep on the voltage of the LED. This LED in this case was 50 volts, and we can switch it on and off at high speeds, about megahertz. And the good thing about this current source is that it doesn't need a rail-to-rail voltage with negative voltage. It can be from 0 to 50, and that's all you need. So I believe this is the biggest contribution of this work, because you can replicate this circuit and you know it's going to be clean transmission from the LED side. Okay, so here is some data on the MOSFET we use, IRF 840, which allows us to do the driving current, but we also need the op-amp, which I told you is not using negative voltage, so it's very handy. And then we have shunt resistor that makes the MOSFET copy whatever voltage we're applying. As we know, LEDs are current driven. So if I give a voltage, it would not always give me the same response. But if I can give a current, it will always give me the same response. So I don't know if you understand how powerful this is, but in terms of power, we're talking about, it's a 20-watt LED panel, so it's not so easy. We saw works before. There is one by one of my colleagues in Spain, Cristo Jurado. He took the same LED panel, but he was switching on and on the driver from the mains. So what happens there is that, yes, you can turn on and off the LED, but you create noise in the electric system. So that's a problem. And also, to make this even more appealing for the new students, this power source is driven by an Arduino and not by a signal generator necessarily. Okay, so it's very handy for you guys. Here is photos of the experimental setup. This is the same camera I was showing outside. We tested different links, but here we present results with 1 meter. It's the same Raspberry camera we've been talking about. And sorry, it's 40-watt LED panel. Yeah. Well, here footprints of the circuit, and we developed PCB with help of people from Portugal. They have good laboratories for building and testing PCBs. And finally, what we take from results is we have a camera 1 meter away, and we're able to receive and decode successfully 180 bits. So it means if I'm doing, for example, visible light positioning, I can have IDs for the LED, about 100 bits. And this means I can efficiently recognize all the IDs in a room. It gives us plenty of room for transmitting data. And in this case, we are transmitting a barcode. That's why you see it's not a square signal as we usually test these systems with. It's a barcode that with the app Othman was presenting in the previous talk, they can do augmented reality. So in this case, with a phone, you point to the source, you see the barcode, and it can sell you products. You can use this in commercial applications. Okay, so the best conclusions of this, as I said, we proposed for the first time the full link. We developed the driver of the transmitter. We used a commercial LED panel, and we demonstrated it was functional for visible light communications. And as I told you, the main contribution, I believe, is with the LED driver, which you can copy for your projects. And we developed this under rigorous testing of the circuit. So I'm confident to say you can use it. We tested this for normal BER. It's the normal metric we use. And we think this is going to be useful for future generations to develop OCC in IoT applications. Thank you very much.
Thank you for your presentation, Vicente. So, any question?
Yep.
I have a question. You can have the second and third slide.
Ah, this one?
One question about the plan.
Mm-hmm.
Which operation amplifier do you use? The normal ones or they don't work?
Yeah, the normal 741, we tried it and we require at least -2 volts. We did also test from 0 to 8 and it worked, but with a high noise. I cannot see the code of the one we finally used, but I know it's in the paper very clearly.
Is it off the shelf or?
Yeah, it's normal bump they gave us in the university. Nothing fancy we had to order from China or something.
Did it have issues with the bandwidth or?
So in the case of OCC, bandwidth usually is limited by the camera. So of course, if we want to go into megahertz, probably this is not the way to go. But for OCC, we're speaking about maximum 10 kilohertz. So pretty capable.
I don't think so. This is very high bandwidth.
Yeah. Yeah.
So maybe that's because it's the high power one. Yeah.
Yeah.
What you want, yeah.
I mean, no, the power is handled by the MOSFET. The op-amp just makes the conversion from the voltage signal to what you need to drive the MOSFET with. So it's more like a follower and not.
You said that you are adding bus.
Mm-hmm.
Thank you. Thank you, Vicente, for your presentation. That topic is very, very related with the work it's doing my undergraduate students at USACH.
Mm-hmm.
We are trying to develop driver that's capable to produce a OFDM signal. So, but it's for positioning purposes. So we have to develop a chip and a tiny devices, not all the VC or all the fancy equipment that is very, very expensive. So the question is, you can produce just square waves with that driver?
This is for switching modulations. Yeah.
And did you find some spikes when you increase the high frequency in current?
So the frequency is quite low, and we didn't see any noise by the circuit.
And do you remember what is the order of the switching frequency?
Yeah, so here with the image is more easy to show. So in one frame, you can read around 1,000 or 2,000 lines. So the frequency of this is, okay, the line shift, it's 20 micro. So it's under 1 megahertz, the frequency of the,
That's a lot.
yeah.
It's high.
Yeah, it's, I mean, for OCC, we're speaking about kilohertz, 10 kilohertz.
Okay.
And so it's always under 1 megahertz.
Okay.
What you need. Yeah.
Okay. Thank you.
Comment about your overshoot or undershoot, which is your domain, is mainly related to your matching. You don't match your systems, your impedance.
Mhm.
That's only critical that if your transient time is becoming comparable to your fluctuation, which means high data rate.
Mhm.
For this sort of application,
It's so slow, you
so
can.
slow,
Yeah.
it just dies away, and you have got ample time to sample the signal.
Exactly.
But be careful, because if you go to the circuit, if you go to the circuit, you can overcome some of those. You see the resistor, the capacitor for the MOSFET.
Mhm.
If you choose that, that acts like fit that, you may be able to reduce your point. Yes.
Yeah.
And also about OFDM, you can modify this easily for analog signals. Yes. OFDM is going to be, if you want to send the analog version.
Mhm.
But you can also convert OFDM to digital. That's
Also, yeah.
section, let's say.
Yeah.
But the idea is to develop a programmable driver. Because if overall in DLP we want to try different modulation and stuff to improve the performance, so we have to construct that kind of driver.
Thank you. And by the way, Othman is here, so you can.
So just to say, it's very interesting. And thank you, Vicente, for covering the presentation. Just to add one point, it's just as Fari was saying that for the spikes of this, you can see these capacitors that we have added in order to tackle this problem. And you can,
You know, it can reduce your bandwidth.
Yeah, it acts as a
I mean,
filter.
The bandwidth is not because we have that op amp and we just have high power in product bandwidth up to 100 meg, and we will not reach 100 meg because we are dealing with less than that. Therefore, we are in a safe state.
Sure.
Thank you.
But the only downside is that you have to be very careful is that if you use, wide bandwidth amps, disadvantage.
Mhm.
Disadvantage, then your SNR will collapse because you're going to have a noise around very wide bandwidth. So you have to be very careful that the first amplifier is got just sufficient bandwidth to allow the signal. Otherwise, you should do anything. So second design, yes.
Mhm.
Thank you.
Thank you. Thank you.
Oh. And yes, who is the next presenter?
Don't hate.
Don't move, Vicente. Stay there.
Don't hate me.
This is the last one. We have two more.
Hello? By guy, are you there? Can you hear us?
Yeah, I can hear you. Not sure.
Okay.
Yeah.
Yes, we can hear you.
Perfect.
Are you ready for your presentation?
Yes, I am. Yeah.
Okay, very good. So you are the next.
Okay, perfect. I'll share my screen.
Okay, so the next presentation is named Data Detection Technique for Screen-to-Camera Based Optical Camera Communication for Bagai Nayaki Yokan. Okay?
Yeah, thank you.
Okay, go on.
Yeah. So, good afternoon, everyone. And I'm sorry, I apologize for not being there in person. So here it's me, Vaige Yoker. I'm from Northumbria University from Optical Communications Research Group, just like Hotman, Fari, and everyone. So my paper and my work is based on data detection technique for screen to camera based optical camera communications. So as I think you can see in my screen, yeah. So today I'll be discussing about the introduction and what we have done and the conclusion basically. So to start with, as I guess it's been for a while, like optical wireless communication, it is something which has recently got the research interest due to few parameters like independent regulation, high energy efficiency, security, and large available spectrum and a long-lasting solution. So currently, I think it's free space communications, visible light communications, and optical camera communications. That has been the major focus of optical wireless communication. So here specifically, I'll be working on optical camera communications. So optical camera communications, so basically we have two types of image sensors. One is a photodiode and second is a camera. And so we have several advantages of photodiodes and camera separately. Camera is basically like an image sensor, which is again formed by an array of photodiodes. So yeah. And there is a diverse range of applications. For example, localizations, augmented reality. We can use it for indoor applications, security applications, healthcare, tracking, smart manufacturing, intelligent transport systems, and digital signage. So these are the diverse range of applications where we can use optical camera communications. So my topic specifically deals with screen to camera communications. And here my receiver and transmitter both are basically smartphones. And that is also because of the overall increase in the amount of smartphones in the day-to-day life. So for my system, it is basically a transmitter smartphone displaying a QR code or a ASCII code or some sort of image, and a receiving smartphone capturing the image and decoding it back to back the data. So here the disadvantages are basically the frame rate, as we know that the screen basically has a higher frame rate when compared to the smartphone camera. So it's like 120 FPS generally for the screen, and the camera works at around 60 frames per second. And the other is also camera resolutions, though they are improved, but it is not like a significant improvement compared to the digital cameras and the hardware capabilities, because if there is also a processing speed which a smartphone can handle, so I cannot really put any high processing application inside a smartphone. So the system block diagram basically of this work covers data, which can be any text data or image data, which will be converted into a binary stream of information, basically like zeros and ones. And out of that, there is an image creation. The image creation is QR and ASCII codes, basically, in my work. And then they are displayed on the transmitter screen. And it is captured by the receiving camera. It is detected, and the image is restored, and the data is recovered back. So here we have proposed a data detection algorithm for detecting the image. So first is the image that is being captured is converted into grayscale. Then we apply edge detection and pixel grouping to the image to improve its visual quality. So these are happens in the internal process, but I have just displayed the pictures. And the third is Hawk transform, which we use for feature extraction. And the fourth is to apply projective transformation scaling so that even if the image is tilted, I can detect its edges. And that's the proposed system for data detection. So for experimental setup, basically I have a transmitter smartphone. Here I'm using a Google Pixel 6 Pro, and that's the same with the receiving smartphone. And here are the features of the displayed image, the refresh rate, and the receiver, the cameras of the Google Pixel, the specifications, and the channel. So here I have performed the experiment in a distance of 0 to 50 centimeter, and the tilt and rotation angle varying for about minus 40 to 40 degrees, and the communication link for now is basically line of sight. So this is my experimental setup, and as for the results, I've converted it and measured it in terms of success rate and distance. So the highest detection accuracy that I'm achieving is around 98%, which is at 10 centimeters, and eventually with the increasing distance, it drops. And the same with the tilt and rotation angles that I took the experimental results in terms of the result session. And then to conclude my work, as we know, OCC is one of the key technologies in the Internet of Things, and then the proposed algorithm is illustrated against varying distance, tilt, and rotation angles. And the third is it has improved. It has overall detection accuracy of around like 98% in line of sight conditions, and it also contributes to the detection techniques and screen to camera communications. So this is my conclusion to conclude the work, and thank you for your time. Any questions?
Thank you for your presentation. Any question? There.
Hello, I'd like to ask, you very briefly went through the angle of rotation that the system is allowed to operate, and also the tilt. So which of the two would cause or would impair the performance more, rotation or a tilt?
Okay. In this condition, as you can see here, in this specific condition, tilt has better performance comparatively compared to the rotation. But here, I also like to mention that I have just rotated and tilted the transmitter smartphone. Like the receiver smartphone is basically stable, so it's like fixed, and
I
it's
see.
only the transmitter smartphone rotating. So
Okay.
yes, in that case, yeah, tilt gives a better performance for detection, but
Yeah.
rotation, I go a lot out.
I would imagine that if you rotate the other device, the result could be different.
Yeah, if I rotate the other device, I
Mhm.
wouldn't be able to capture for these many angles.
Mhm.
It would be
Yeah.
very much restricted to around 15 degrees because the camera will go out of focus.
Okay.
Yeah,
Thank you.
thank you.
Any question? No? Okay. Thank you very much for your presentation.
Thank you.
Okay, now let's move on for the last presentation.
Me again.
Yes. Asynchronous encoding scheme for optical camera communication system using two-dimensional classifier.
Hello, everybody. Thank you, Diego. Well, yeah, let's move on quickly. This work is by Dario Fernandes from Portugal. He works at Instituto de Telecomunicações in Aveiro with Professor Luis Nero Alves. I apologize, he cannot attend the meeting, but I'm here to cover fourth person. Okay, so I will try to go quickly into the end, because I believe the best contribution of this work is what we called the differential communication. But of course, we need to talk about how this setup was made. So our goals is to communicate first LED matrix, 8 by 8 LEDs with RGB capability to a camera. Okay. We need to construct codes that we will transmit from the LED, and we call these codes alphabets. So all the possibilities you can send and how they will benefit or impair the communication. Then we will compare these alphabets and explore this novel asynchronous method for differential communication. So one of the main problems, and I heard it from questions in the coffee break, what happened with a camera that receives frames that are not equally spaced in time. So the camera is labeled as 30 FPS, but then I see in what time they are captured, and they do not respect this frame rate, okay? So this is what we try to overcome with this system. Yeah. So as I said, we have first microcontroller. sending PWM signal to the LED matrix. We also have in this microcontroller little Wi-Fi where we can set what alphabet we're using. Then this alphabet is being presented to the camera. We record video with Raspberry Pi. And then I hope you know YOLO is you only look once. It's a deep neural network for recognizing patterns. It's very popular in the face recognition fields, but now we're using it for communication. And the way we define our alphabets is, okay, first we count on all the LEDs, but to make it a bit more simple, we only use green channel for communication. And what we realize, I will show you afterwards, is yes, when we use all LEDs, we have more possible symbols, but we need to take into account what happens if I rotate the image, similar to the problem before. Some symbols need to be discarded because they are the rotation of another symbol, so they are not different for YOLO in this case. And similar to QR and also Aruco markers, if you know, QR codes, they use 3 blocks to determine what is the actual orientation. So we took this idea and we made an alphabet with a little dark corner and also a frame in red that helps the system to tell what is the orientation of our LED. And that's how we can make this and this different symbols instead of having this and this the same symbol because they are rotated. Okay, so this is alphabet 1 and 2. We present the alphabet to the camera and we record different situations, distances, reflections. I think I have an image for that. Yeah. So we choose different distances, different SS stands for shutter speed, but it actually means the exposure time of the camera. So here is longer exposure, shorter exposure, same distance, but different lighting. So we have dark room or with artificial lights. And finally, we do more distance. So we create various data sets, making all these different changes, because the idea is that this system in many different situations will be able to receive the information. We also tilt the transmitter. We put it in front of a window, so we have a lot of noise. And we try also this noise with larger distances. I want to point out that this reflection here, when Dario was presenting this to the ECRN, they asked him what happens with this reflection, and he actually discovered that this was a very important thing to take into account. So I want to promote ECRN for helping us detect what we cannot see because we're busy with all the details and some obvious things are skipped. Okay, so average precision in a neural network for recognizing patterns, it's very well known in, as I was telling, with YOLO and other systems. So we need the artificial neural network to recognize where is my symbol, and usually it gives us a square. And this square is compared to the real square where the information is. And if there's a little mismatch, we have intersection that is smaller than the actual squares. And with this information, we develop the average precision, which is shown here. Basically, more is better. Okay, and epoch is how many iterations we have done over the whole dataset. Okay, so here what we show is basically that we have 3 datasets that can be recognized with our system. So after a lot of testing, we have a system that is efficient at segregating what is the actual information in the frame. And now we can move on to what's important for this paper is the differential communication. So most of us are familiar with what is, for example, a constellation. Usually, if I want to send 2 bits per symbol, I need 4 different symbols to convey this information. So usually these alphabets are a power of 2. So I have n to the power of 2 different symbols. And what we came up with is, first, we want to have the ability to not necessarily be synchronized with the camera, because sometimes you make photo, then you make the next photo, and if it was the same symbol, you have no idea if this is actually a different symbol with the same information, or they are exactly different symbols from the transmitter. Okay, so we bound our system to find transition from one symbol to the other, and that's how we know we are making a new sample. Okay, and then with the alphabet size and the number of transitions I need, we can play with how many different letters in the alphabet, let's say. Okay, so we are not bound to have n to the power of 2. We can play with m, which is the number, the size of the alphabet, and p, the size of the arrangement, and we can have different data rates. So here in this example, we have A and B, these are our 2 symbols, and I wait for one transition to get my information here. So when I go from A to B, I have 1 bit, then I see A to B again, and I have another bit, and so on. Okay. Here, after simulating, we demonstrate that when we're using a power of 2, our system is worse than using normal, for example, M16 would be 4 to the power of 2. All right, yeah. So for 4, it's better to have the conventional method with power of 2, but for anything that is not power of 2, we have better performance. Okay. So after this part of the differential, we also have oversampling, which is the following. Our LED matrix is switching slower than the capture rate of the camera. The camera has 30 frames per second, or 30 hertz approximately. And the frame is at least half slower. Okay, so in this case, we chose 10 hertz. And what happens is that when the matrix is refreshing, we lose some frames. And the one we take, we know that if the next photo is the same frame, it's because we are in the same frame here, because we are only looking for changes. If it was the same frame, we know we're inside the same symbol. Okay, so here we have 2 useful frames, which is one that gives me the information. The other one confirms me that I'm in the same transmission, and then I lose 2 because of the transition, and I get the new one, which allows me to compare and get new information. So in this way, we have not to be synchronized to the camera, and we can still transmit data. Okay, so the main conclusions is that comparing all the alphabets we use, the matrix identifier was the best because it gives us the orientation of the LED matrix, as demonstrating with this average precision metric. Then we have to consider what happens with the reflections, because they give us exactly the same symbol but reflected. So it's very important to consider what happened with the reflections. And then the main contribution, in my opinion, is this differential communication with oversampling that allows us to synchronize with data efficiently. Okay, so this system is worse than power of 2 when I'm using power of 2 alphabet, but the arrangement size help us to play with different data rates. Okay, that's.
Thank you, Vicente.
Thank you.
Any question? Everyone is tired.
Yeah, I'm sorry.
Yeah, tired of it.
Yeah, I know.
Well, no question? Well, very interesting presentation, Vicente.
Here.
Okay, good.
I have a short question. I don't
Yes.
understand, why do you need two colors? Is it just to make the neural network job easier?
Yeah, we could use the three colors, RGB, but for first attempt, we are actually using now RGB inside what is called the frame or the dead zone. So we use the red to give the orientation, so the neural network knows how it's oriented, and this is fixed, is always red. And then inside we can use whatever color we want. We just use green because when you transform green into grayscale, it gets more intensity than pure red or pure blue.
But why not just a single color? Like make the border green, for example.
Like QR codes, yeah, it could be like black and white on and off, but we have three colors, so yeah. And we had
Thank you for your presentation.
Thank you.
You didn't mention, I don't know if you mentioned the size of your data set.
Yeah, I didn't mention that. It's very important. I think it's not in the presentation, but it's around thousands of image for, so one is 1,000, then we did 2,000, not exactly, but around that. Yeah.
Did you try any other model like conventional CNN to classify your?
No, I know well, I'm not expert in that part. I know YOLO-X is not the most recent or the most efficient, but one important thing to take into account is we're running this in a Raspberry Pi, and so it's not very resourceful in terms of RAM and CPU capacity. So I believe, I might be wrong, but I believe YOLO-X, the X stands for like a reduced model that can run in the Raspberry Pi.
Do you have any plans to publish the data set?
Yeah, it's publicly available. Dario has GitHub, I believe. If it's not uploaded yet, we can share it, no problem. Yeah.
Thank you.
Thank
Good
you.
news.
Thank you very much.
Okay, so this is the end of the day. Thank you so much for everybody. See you tomorrow.